Hello and welcome to Sleepy Science. I'm so glad you're here. Tonight, set your mind down like a glass of water on a quiet nightstand and walk a calm path through quantum information. We'll feel what a qubit really is. Gentle amplitudes rather than hard bits. Then let the Bloch sphere give that feeling a shape. We'll weigh uncertainty with clear entropy measures and spend mutual information like careful coin. Limits will steady us. The Holevo bound tells what messages fit, while Schumacher's compression shows how to pack states without creasing them. We'll respect firm rules. No cloning, no deleting. Then try graceful moves. Teleportation that relocates a state without moving matter. And superdense coding that tucks extra meaning into one traveler. When noise arrives, we'll purify weak links into strong ones and stitch protective quilts. Error correction, fault tolerance, stabilizer thinking, and the geometric comfort of CSS and topological codes. To compute broadly, we'll fuel up on magic states. And to measure softly, we'll budget coherence like breath. Trust will come from patterns, not promises. Bell tests to certify honesty, expansion that turns a spark of randomness into a river, and one-time pads with secret sharing that hide value in relationships. If we outsource, we'll wear masks, blind computation that reveals work but not intent, and we'll ask whether location can be a key, how money could be unforgeable by physics, and why tomography must listen for whispers in the walls. We'll learn the borders drawn by information causality, separate heat from harmony by telling thermal entropy from entanglement's boundary songs, watch the page curve bend toward unitarity, and see the Petz map unscramble what wasn't truly lost. We'll treat complexity as a resource to budget, rest states where they last, spins, ions, photons, and sketch a first quantum internet, an entanglement supply chain that carries togetherness across a sleeping city. If this gentle wander helps you rest while learning, please like and subscribe so more sleepy minds can drift here. Now breathe slowly, feel your weight supported, and let curiosity idle in low gear. We'll go far tonight softly. Qubits. Amplitudes, not bits. You start by listening to a quiet room because a qubit begins as quiet possibility rather than a loud decision. A classical bit is a light switch, up or down, 0, 0 or 1, while a qubit is more like a dimmer set to a very precise angle with a tiny compass attached. And what matters isn't only how bright it is, but which way its hidden arrow points. Because in quantum mechanics, the world is described by amplitudes, not bare yes, no answers. And those amplitudes carry two pieces of information at once. How strongly a result is favored, and the direction that decides how different possibilities combine. You don't get to open the hood and read amplitudes directly. You only get measurement clicks, this or that. But if you repeat an experiment many times and pay attention, you notice patterns that reveal the invisible geometry underneath. Like listening to waves you can't see by the rhythm they drum on the shore. At first it's tempting to say, a qubit is both 0 and 1, yet that's too sloppy. Because a qubit isn't a coin stuck mid-air, it's a controlled recipe that tells the universe how to weigh and orient outcomes, so that when different paths meet, they can add to each other or wipe each other out. The way two ripples on a pond can build a taller crest or flatten into calm water, depending on whether their peaks align or oppose. And this ability to interfere is the qubit's superpower. The reason it's not just a fancy bit, but a different animal entirely. In practice, you prepare a qubit by guiding some physical system into a chosen superposition, maybe the magnetic orientation of an electron's spin, the energy levels of a superconducting circuit cooled near absolute zero, the presence or absence of a single photon in a specific path, or the internal states of an ion floating in an electromagnetic trap. And then, you let it evolve through carefully designed operations called gates, which are just actions that rotate that little amplitude arrow in controlled ways. If two operations push the arrow in the same direction, the chance of a chosen outcome increases. If one undoes the other, the chance fades. And because the arrow remembers its direction, order matters. So doing A then B isn't always the same as B then A. A clue that quantum change is more like choreographing a dance than flipping a series of switches. When you finally measure, the soft cloud of possibility snaps to a single outcome, and the statistics over many trials reflect the squared length of those hidden arrows. That squaring rule is a distinctive fingerprint of quantum theory, and it's what turns the elegant but unseen amplitude story into the hard counts and experimenter records. Importantly, what you call phase sets relative orientation, which means only differences in direction between alternatives have physical bite. If you shift every arrow by the same amount at once, nothing changes. So the qubit cares about relationships, not absolutes. A small but profound hint that information in the quantum world is fundamentally relational. Because amplitudes interfere, you can design sequences that make one answer almost inevitable and another nearly impossible. Not by stacking probabilities, but by steering those arrows through spaces where they reinforce or cancel. Think of threading a marble through a maze whose corridors are invisible but real, where turning a knob here and tilting a mirror there guides waves, not marbles, so that only one exit glows. This is why simple demonstrations like single photon interferometers feel almost spooky. Block a path, and the pattern on the screen changes even if the photon could have taken the other route, because what you blocked wasn't just a lane, it was a contribution to the amplitude that shaped the final statistics. Working with qubits then becomes a craft of coherence. Keeping that delicate arrow from smearing out due to unwanted jostling from the environment. Stray heat, vibrations, electric noise, or random atoms bumping around can leak which-way information into the surroundings. And once the outside world learns too much, interference fades, a process called decoherence, after which your qubit behaves more like an ordinary bit with ordinary ignorance, rather than a wave of structured possibility. This is not a philosophical footnote, but an engineering wall, because to build useful quantum devices you must isolate, shield, error correct, and operate faster than nature can blur your arrows. Notice how this picture quietly reframes what computation means. On a laptop, you march bits through logic gates that tally and compare, but in a quantum circuit, you choreograph amplitude arrows so that the wrong answers cancel themselves and the right answers add up. A kind of algorithm by interference. It's not that a qubit tries all answers at once in the sci-fi sense. It's that you shape a wave over the space of possibilities and use interference to sculpt that wave toward a pattern you can read at the end. And the success of any algorithm depends on whether you can arrange the landscape so the desired peaks are high and the undesired valleys shallow or gone. If you're wondering why we don't just peek at the arrows as they dance, it's because peeking is precisely what destroys the choreography. Measurement extracts a definite fact by forcing the system to choose, and in doing so, it wipes the delicate phase relationships that make the dance meaningful. That trade-off isn't a limitation of our tools, but a rule of the world, one that has been checked in countless experiments from double-slit setups with single particles to modern chips that run thousands of gate operations before the environment wins. You can delay measurement, erase path information, or recombine routes in ever smarter ways, and the statistics will follow the amplitude book each time. A helpful way to think without equations is to picture a compass needle living on a tiny sphere, where north and south represent the sure outcomes you can test, and every other point is a different blend with a different phase. Rotate the needle and you change what likely means for a chosen test. Pick a different test and you've changed what counts as north. That interplay between preparation, transformation, and the particular question you ask at the end is the essence of qubit behavior. And it's why the same state can look certain to one measuring device and uncertain to another. Not because the state changed, but because certainty is always defined relative to a basis, the lens you chose to look through. Although popular language says the qubit is both, a better habit is to say the qubit is prepared so that different answers have amplitudes with specific sizes and directions, and those directions decide how answers cooperate or fight when paths meet. Because that phrasing keeps you honest about what we can and cannot claim. It protects you from thinking of the qubit as a hidden tiny coin or a tiny classical wave, and reminds you it is a rule for combining possibilities that only turns into facts when we insist on an answer. You'll also meet coupled qubits and the strange correlations they can share, but resist the urge to jump there yet. The single qubit already teaches the core lesson. Nature allows a structured superposition with phases that steer outcomes through interference. Measurement translates amplitudes into probabilities by a precise rule, and the environment can wash away the structure if we aren't careful. Master that. And the more spectacular tricks later: communication protocols, error correction, secure randomness, make sense as careful games played with arrows rather than switches. So when you hear amplitudes, not bits, let it slow your mind in a good way. Imagine a silent dial you can set to sculpt how the future unfolds across repeated trials. Imagine that what matters is not only how much of each outcome you prepare, but how the pieces line up. And imagine the craft of quantum technology as learning to draw with phase and length in a space your eyes can't see, but your instruments can honor. If you can hold that picture gently, you already carry the seed of why qubits are both fragile and powerful, and why the real magic is not mystery for its own sake, but a deeper kind of control over possibility itself. Bloch sphere, geometry of knowing. You learn the shape of certainty by picturing a tiny globe in your mind, not the Earth, but a sphere that stands in for everything a single qubit can be. And as you slowly rotate it between your fingers, you notice a rule. Each point on this sphere is not a place in space, but a way of answering a yes or no question with a bias that depends on direction. The North Pole means you are as sure as you can be about one answer. The South Pole means you are as sure as you can be about the opposite. And every other point between those poles carries a tilt of confidence that shifts as you turn the sphere. Because the geometry here is a geometry of knowing. The latitude tells you how strongly one outcome is favored over the other, while the longitude encodes a hidden alignment that only shows its power when you choose a different question to ask. And the remarkable thing is that all of this, preparation, change, and readout, can be described as simple rotations of that point around the globe. If you fix your question to up or down along a chosen axis, the closer your point drifts toward the North Pole, the more often you will hear up when you measure. And as the point slides toward the equator, your answers become balanced, then tip toward down as you approach the south. Switch the axis of your question, and you have effectively spun the globe under your pointer, changing which regions mean certainty and which mean doubt. So the same physical state can look definite to one test and undecided to another, not because it changed into something else, but because knowledge in the quantum world is always defined relative to the direction you look. This map is powerful precisely because it hides details you do not need. Global twists that never affect any outcome are collapsed away, leaving you with just two coordinates that truly matter for a single qubit. How much the answers are weighted and how the waves of possibility are aligned relative to each other. Think of latitude as the balance knob between the two outcomes you plan to check, and longitude as the alignment mark that decides how possibilities add or cancel when you rotate your question. 2 points on the equator may look equally balanced for your original test, yet they can behave very differently when you turn the apparatus 90 degrees, because their longitudes, those alignment marks, were never the same. When you perform an operation on a qubit, you are not pushing a particle along a track. You are spinning a point on this sphere around an invisible axis, and whole families of real hardware, from trapped ions to superconducting circuits, are engineered to deliver clean, timed rotations. A short pulse tilts the state a few degrees. A longer one carries it to a new latitude. A carefully phased pair sends it along a great circle route like a geodesic flight. Compose 2 rotations, and you have drawn a triangle on the surface whose corners remember the order you visited them. A visual hint of why doing one action then another is not always the same as reversing them. The sphere also teaches you how measurement sows possibility into fact. Choosing a measurement is choosing which axis pierces the sphere. Projecting the point onto that axis yields the odds of each answer. Repeat the experiment many times, and the relative fraction of yes outcomes mirrors how far north you were. Swing the axis, and you redraw the map of certainty. This is why calibration begins with simple scans that move the axis and watch the statistics, letting you locate the state's position with 3 gentle probes, one for each principal direction, much like finding your latitude and longitude by sights on the sun and stars. The most sobering lesson arrives when the point refuses to stay on the surface. Ideally, pure states live on the skin of the sphere, bright and fully stretched, but stray heat, stray fields, and tiny leaks of information into the environment tug that point inward. Your once crisp arrow shortens as if made of rubber, sliding from a sharp tip to a blunted one near the center, where no direction gives strong guidance. This is not mere ignorance from your side, but a real loss of usable alignment called decoherence. And different kinds of noise leave different geometric fingerprints. Some smear longitudes while leaving latitude mostly intact. Others pull everything toward a particular pole, and still others crumple the sphere in lopsided ways. So debugging a quantum device often means watching which shapes shrink and which survive, then designing pulses and protections that push the point back out to the surface. Notice how much clarity you gain from this simple picture. Opposite points on the sphere represent states that your chosen test can always tell apart in a single shot. Neighboring points represent states that no clever trick can perfectly distinguish without paying a price. Shortest routes on the surface correspond to efficient control sequences. Elegant symmetries on the sphere translate to robust tricks in the lab. And mixed states, those duller points inside, remind you that certainty is not a property you own, but a resource you must guard. Even ideas that sound abstract become tangible here. Learning a state is like surveying the globe with 3 compasses. Erasing unwelcome alignment is like averaging many longitudes until only latitude remains. Protecting information is like locking your point to a path that noise cannot push you away from. And composing gates is like planning flights that minimize turbulence by hugging great circles, rather than zigzagging through unnecessary detours. Perhaps the most disarming insight is philosophical. This sphere is not the world. It is a map of how you come to know the world. Rotate your question, and meaning rotates with it. Align your controls, and possibility carves new grooves across the surface. Let the environment listen too closely, and the surface itself recedes. After a while, you realize you are not just moving a dot, you are curating a relationship between what there is and how you ask about it. So take a slow breath, and hold the globe still in your imagination. North and south promise sharp answers. The equator hums with balance. Longitudes hide the choreography that only appears when you change your view, and the center warns what happens when you let the outside world do the asking for you. This is the Bloch sphere's quiet gift, the geometry of knowing showing you, without equations, how preparation, action, and inquiry braid together to make certainty, and how gentle control can turn a fragile point of light into a faithful guide through the strange but navigable country of the quantum. Entropy measures, von Neumann to Min-Entropy U. Learn to weigh uncertainty the way a careful traveler weighs luggage, not by staring at the suitcase, but by asking how many outfits you could pack inside it. And in quantum theory, that weight is called entropy, a family of measures that tell you how much reliable structure you have and how much is fog. At one end is the von Neumann entropy, a calm yardstick for a single quantum state that has possibly been touched by noise. And it reads 0 when your state is as sharp as it can be and climbs as that sharpness frays into mixtures. So if your qubit is a crisp point on the surface of the sphere you met earlier, the dial sits at 0. But if it sinks inward under heat and listening ears, the dial rises, telling you that certainty has been traded for options. What makes this measure special is its operational meaning. It sets the ultimate rate at which you could compress many copies of a quantum source without losing the essence, the way a good packer learns which folds preserve shape and which just waste space. And in bipartite systems, it turns into a measure of entanglement for pure states, counting how many pairs of perfectly linked qubits you could distill if you had an infinite patience and flawless tools. It also obeys strong rules that keep your reasoning honest. Merge 2 systems, and entropy doesn't do acrobatics. Process a state through a noisy channel, and it never becomes easier to learn about it than before. Split information into parts, and you can't beat the triangle-like inequalities that tie those parts together. So, entropy is not only a number, it is a map of what you can and cannot do. Yet knowing the average shape of your uncertainty is not enough when you face an adversary or a rare catastrophe. That is where a broader family steps in. The Min-Entropies, which scan your ignorance from different angles. Some emphasize the common cases, others the tails, and among them, the Min-Entropy plays the role of a stern parent who cares only about the worst case. If someone tries to guess your outcome in a single shot, Min-Entropy says how likely their best guess can be, so higher Min-Entropy means no single outcome is dangerously predictable. This matters in cryptography. because a lock is only as strong as the easiest path through it. And min-entropy speaks the language of best-guess attacks, not average comfort, which is why modern quantum security proofs lean on it the way climbers lean on the firmest holds. In the real world, your data and your qubits are never isolated. So you measure entropy not just for a system, but conditioned on whatever an observer or an eavesdropper might hold. Here, quantum theory reveals a twist you don't encounter in simple dice games. Conditional entropy can turn negative, which does not mean information is less than nothing but that, with the right entanglement. Knowing one side lets you predict the other more precisely than any classical correlation would allow, a resource that shows up in tasks like state merging, where you pay or earn information currency to move quantum states from one hand to another. The positivity of relative entropy and the deep property called strong subadditivity keep these trades consistent, and together they guarantee that processing information locally cannot conjure knowledge from thin air, because experiments never happen once but across blocks of signals drenched in noise. You also meet smoothed versions of min-entropy and its sibling max-entropy. You are allowed a tiny tolerance for rare events, and within that margin you ask, how unpredictable is this really? A beautiful bridge then appears called the quantum asymptotic equipartition property, which quietly promises that as you study longer sequences drawn from the same source, the smoothed min-entropy per copy drifts toward the von Neumann entropy, uniting worst-case thinking with average-case thinking, the way long walks make you trust the shape of a path. That bridge is the backbone of practical protocols where you must turn messy raw data into uniform secret bits. In secure randomness generation, you begin with measurements that are partly predictable and partly influenced by unknown devices or even quantum-savvy adversaries. The min-entropy tells you the minimum number of clean random bits you can possibly extract, and the leftover hash principle, stated without formulas, says that if your min-entropy is high enough, then a short, carefully chosen hash of your data looks fresh and uniform, even to someone who saw everything else, including any quantum memory they kept. This is what allows quantum devices to produce public randomness with certificates, and it is why laboratory systems chase not only average entropy, but provable min-entropy under realistic models. In communication, entropy measures draw borders. The Holevo limit, expressed through the same von Neumann dial, caps how much classical information you can squeeze out of quantum states, no matter how clever your receiver is, reminding you that quantum carriers are not loopholes to infinite bandwidth. In compression, Schumacher's theorem uses the same dial to tell you how many qubits per signal you truly need to store a source with vanishing loss, making entropy the ruler in your packing list. And in thermodynamics, the logic aligns with Landauer's lesson that erasing information has a physical cost. So when your entropy drops because you reset memory, heat must bloom somewhere else. An anchor that keeps abstract notions honest by tying them to energy and temperature in the lab. You also rely on continuity. Small changes in your state cause only small changes in von Neumann entropy, so calibration errors don't make your estimates swing wildly. You rely on monotonicity under processing, which says side channels cannot increase your certainty about a system unless they already had it. And you rely on chain rules that let you bound the entropy of a whole by stitching together the parts, crucial when you assess security proofs that span dozens of steps and devices. The deeper you work, the more you see that each member of the entropy family answers a slightly different question you will actually ask. Von Neumann entropy asks, how compressible is this source? Or how mixed is this state? Conditional entropy asks, how much remains to be learned if a helper whispers everything they know? Mutual information, built from the same pieces, asks, how aligned are two systems? How much can one tell you about the other? And min-entropy asks, what is the most an opponent can guess in one unfairly lucky shot? Choose the wrong measure and your protocol may look safer or faster than it truly is. Choose the right one, and the limits become clear enough to design around. Perhaps the most human way to hold all this is to imagine standing at a crossroads with fog of varying thickness. Average fog helps you plan a long journey efficiently. Worst case fog tells you whether you dare step onto the next stone at all. and conditional fog describes what clears if a friend signals from the hill. Entropy is not mystery for its own sake. It is a toolkit for honest promises. And in quantum technology, where possibilities can cancel and align in ways you never see directly, these measures are how you decide what can be saved, what can be shared, what can be kept secret, and what must be paid for. Hold that gently, and you will feel why the path from von Neumann to Min-Entropy is not a march through jargon, but a single lesson in many voices. To control the future, you must first measure your uncertainty in the right units, and then guard the pieces of knowledge that matter most. Mutual information as correlation currency. You can think of knowledge as a kind of money that only exists between things, and mutual information is that currency, the amount of uncertainty that disappears about one variable when you learn the outcome of another. So if you and I look at the same scene from different angles and compare notes, the overlap in what we can predict about each other's observations is our balance. This is not a vague metaphor, but an operational measure. It counts how many yes-no answers you no longer need to ask once someone whispers their result. And it is symmetric because shared structure doesn't care who speaks first. In a clean world, two perfectly synchronized clocks have a high balance, while two unrelated dice rolls have none. And everything interesting in science and engineering lives in between, where structure is present but mixed with noise. The beauty of mutual information is that it treats patterns as patterns no matter their shape, linear or not, smooth or jagged, so it can detect alignment that ordinary correlation misses, making it a powerful detector of hidden relationships in biology, language, images, and signals. In communication, it becomes the accountant that decides how many reliable bits you can send through a noisy channel per use. When you choose the best way to speak, it says, on average, by how much does the receiver's uncertainty about the sender's message shrink after listening? And maximizing that shrinkage defines the channel's capacity. The honest speed limit for error-free transmission with smart coding. If the channel is a pipe, mutual information is the water actually delivered, not the water poured in, and noise is the leak that forces better seals or lower flow. This is why modern codes don't fight errors symbol by symbol, but instead approach capacity by spreading messages across long blocks where structure can be recovered. And the performance is forecasted not by wishful thinking, but by the mutual information budget the channel allows. In learning and data science, it plays the role of a fair buyer. A feature is valuable if it reduces uncertainty about the target you care about, and mutual information measures that value without caring whether the link is linear, monotonic, or tangled. It helps choose sensors in an experiment, pick variables for a model, or decide which training examples carry new insight, rather than repeating what you already know. Because this currency cannot be forged locally, the data processing inequality tells you that any post-processing of the data, no matter how clever, can never increase the mutual information with the truth. All you can do is spend it more wisely, a humbling principle that explains why overfitting feels powerful in practice, but buys no new reality. It just relabels the same budget in louder colors. In networks, it becomes a traffic rule. If information flows through a chain A, B, C, then the shared structure between the ends can never exceed what passed through the middle. Bottlenecks are real because this currency cannot teleport. You can compress, re-encode, or filter, but you cannot mint extra alignment downstream without touching the source. That's why the information bottleneck method works. By forcing an intermediate representation to carry as much relevant mutual information as possible with the target while discarding irrelevant details, you build models that generalize rather than memorize. In neuroscience, when a neuron spikes more reliably for one kind of stimulus than another, the spike train holds mutual information about the world. Experiments measure how many bits per second are carried by a cell and how that budget changes with attention, adaptation, or disease. In genetics, regulatory elements are sought by the structure they share with expression patterns. In privacy, the mutual information between a released summary and the secret dataset is a leakage score, how much an adversary's uncertainty shrinks after seeing the report. So designers aim to limit that budget by injecting carefully calibrated noise or by releasing coarser views. In thermodynamics with feedback, the currency becomes literal work. A controller that learns about a microscopic system can do better at extracting energy from fluctuations but the gain is bounded by the mutual information it acquires. Maxwell's thought experiment is settled by a counting that includes the demon's memory, and once you pay for erasing that memory, the books balance. Knowledge doesn't cheat the second law. It just converts structure into capability with a receipt. The quantum world deepens the story. The quantum mutual information between two systems counts total correlations, both the ordinary kind and the uniquely quantum kind, and it sets limits on tasks like how much work two parties can gain by cooperating, how much noise a channel must add, or how much entanglement has been generated or lost. If two labs share a state and perform only local actions, their mutual information cannot grow unless they communicate, anchoring security proofs and resource theories in a single number that refuses to be fooled. Importantly, not all shared structure is equal. Some is purely classical, some is quantum and fragile, and finer tools like Discord split the bill, but mutual information remains the top-line figure that no decomposition can exceed. Day to day, you estimate this currency from data. Count how often pairs of outcomes co-occur. Compare that to what you'd expect if they had nothing to do with each other, and average the surprise. With continuous signals you bin, smooth or fit models to approximate the underlying distributions, mindful that bias and variance in estimation can invent or erase apparent structure. Robust workflows use cross-validation, surrogate tests, and bootstrapping to ensure that the money you think you found isn't just a mirage of small samples. When you move from pairs to groups, total correlation and interaction information begin to separate redundancy. Many sources echo the same fact. From synergy, only together do they reveal something new, guiding sensor placement and ensemble design so you don't pay twice for the same clue. Perhaps the most practical way to carry this idea into your work is to ask 3 questions before you collect or compute anything. First, what uncertainty truly matters? Define the target variable whose fog you want to thin. Second, which knobs can I turn that might align with it? These are your candidate features, sensors, or messages. And third, where are the bottlenecks? Points in the pipeline where mutual information can only fall. With those answers, you can trace a path from source to decision and check at each step whether your transformations preserve the currency or waste it. You will find that many arguments evaporate when reframed this way, because mutual information doesn't care about favorite models or pet theories. It cares about the actual reduction in not knowing. In the end, thinking of mutual information as correlation currency is freeing. It reminds you that knowledge is not a property of one object, but of a relationship. It tells you that cleverness after the fact cannot outwit a narrow pipe. It invites you to spend your budget where it matters most and to protect it from leaks you can't repair later. And it leaves you with a simple, rigorous habit. Measure how much surprise disappears when two things meet, and let that number, not the noise of preferences, guide how you design experiments, build codes, choose models, and make promises that the world will let you keep. Holevo bound. Limits on quantum messages. You sit down to send a message and feel greedy. If a qubit can point anywhere on its little sphere, shouldn't it carry a river of meaning, more than a plain on-off? And the Holevo bound is the sober answer that keeps your expectations honest. No matter how many clever states you pick, or how artfully you measure them, there is a hard ceiling on how much classical information you can reliably pull out of quantum signals, a ceiling set not by optimism, but by the geometry of distinguishability. The bound says that when you choose a set of quantum states to represent different letters, the most knowledge any receiver can gain about which letter you sent is limited by how those states spread out in the space of possibilities. And if they overlap, if they are not perfectly orthogonal, some confusion is unavoidable and no measurement can undo it. At heart, the bound draws a clean line between what feels possible when you imagine phases and amplitudes as endless dials and what actually lands in the lab as bits you can bet on. Picture a simple game. You and a friend agree on a codebook. For the letter A, you'll prepare one state of a photon, for B another, and so on. You send many signals down a quiet fiber, and your friend at the other end chooses the best possible measurement to guess each letter. If all your code states are orthogonal, your friend can learn each one perfectly. No ambiguity, full recovery. But the moment you slip non-orthogonal states into the alphabet, there is an irreducible blur, and the Holevo bound turns that blur into a number, an upper limit on the average number of yes-no answers your friend can save by listening. It doesn't tell you how to measure. That's a separate task. But it tells you how well any strategy could ever do. Even if your friend uses the most general kind of measurement allowed by quantum physics, including collective strategies that touch many signals at once. This limit has a second, almost shocking consequence when you first hear it. A perfect qubit channel, no noise at all, still cannot carry more than one classical bit per use unless you bring in outside help. That's because only two states can be perfectly distinguished in a two-dimensional space. So your richest, smoothest wave of possibilities collapses at the receiver into a simple either-or once you demand definite letters. Phases that feel abundant at the transmitter are not a secret backdoor to extra alphabet size if you need error-free reading at the other end. You can, of course, send long blocks and let the receiver perform joint measurements across the whole block. This often approaches the limit that the Holevo bound permits, but the per-use rate for a clean qubit line still tops out at 1 bit in the long run. If you're tempted to protest, "But I heard we can pack more with quantum tricks," you're thinking of a different resource, prior shared entanglement. With an entangled pair already split between sender and receiver, the combination of that shared resource and a qubit through the channel enables 2 bits per channel use, a protocol famous for its elegance. But notice what you spent. You burned a separate, precious link to double the classical rate. The Holevo bound itself stays loyal to the same accounting principle. No channel can summon more accessible classical information than its structure allows, and any apparent extra must be paid for by something you had beforehand. In the messy world of noise, this ceiling is even lower. Channels that randomly rotate, absorb, or mix your states shrink the space of distinguishable possibilities, and the bound keeps pace, telling you before you write a single line of code how much you could ever hope to squeeze through with vanishing error using the smartest block codes and the most patient decoders. It is the quiet converse to optimism. Design codes that approach capacity, yes, but never promise a rate the bound forbids. This is why practical quantum communications begin by characterizing the channel and estimating the best possible alphabet and input distribution, because the choice of which states to send already decides the budget of clarity available to the receiver. The Holevo bound also clarifies a common misunderstanding that swirls around quantum talk. You might think, since amplitudes are continuous, can't I hide an infinite message in a single system by dialing the phase with exquisite precision? But at the point of readout, when the receiver must produce definite classical answers with low error, the game is not about how finely you set a knob, but about how sharply the receiver can separate the options. If two states are close, any measurement that tells them apart will sometimes fail. And when you average across many uses with real noise and finite data, the bound reappears as an iron budget. The richness of quantum states is real and powerful for other tasks, like computing by interference or verifying non-classical correlations, but for the act of classical messaging, the receiver's knowledge has a limit that extra flourish at the transmitter cannot surpass. There is a deeper reason this feels so right once you accept it. Information is not a property of a single object, but of a relationship between preparation and question. And in quantum theory, that relationship is constrained by the same rules that govern uncertainty and disturbance. The measurements that extract the most about one set of signals are the very ones that erase distinctions important to another set. So you can't choose a single measurement that reveals all patterns at once, and any code that leans on one geometry pays a price in another. The Holevo bound packages that trade off into a single line on your design whiteboard. Choose your alphabet and your channel, and the maximum mutual alignment between what was sent and what can be learned is capped. Build within it. This is not bad news. It is a gift of honesty that lets you design systems that are as good as physics allows. It tells you when block measurements are worth the effort, and when simple, per-symbol reads are enough. It tells you why mixing too many nearly overlapping states to cram more symbols into your alphabet backfires, because the bound doesn't care about how many labels you invent. It cares about how well the receiver can separate them. It also underwrites security arguments. If an eavesdropper intercepts your signals, the same ceiling constrains how much of your classical payload they can learn without introducing detectable noise. And that limit, paired with careful public discussion afterward, is what lets certain key distribution schemes prove secrecy against powerful adversaries. Day to day, engineers feel the bound as a compass rather than a cage. They probe channels, estimate how distinguishable candidate states remain after the trip, and compute the best achievable rate. They learn to build alphabets whose states are as far apart as the physics permits, to align the transmitter's choices with the receiver's most revealing measurements, and to avoid wasting power on fancy encodings that look rich at the source, but collapse into ambiguity at the destination. And theorists use the same compass to prove coding theorems, showing that there exist families of codes that asymptotically reach the ceiling, though doing so may require collective measurements across long blocks. Hard in practice, but illuminating, because it means the ceiling is not just a warning, it is a target you can aim for with enough craft. In the end, the Holevo bound is a gentle correction to our early excitement. Quantum systems can be prepared in endlessly varied ways, but when the task is to send letters that must be read out loud and unambiguously, the world pays attention to one question: how well can the receiver tell the possibilities apart? And it answers with a limit that has proven unshakable across decades of theory and experiment. Carry that limit with you like a budget line, and you'll design quantum messages that are bold yet honest, ambitious yet feasible, respectful of the difference between the shimmer of a state at the source and the solid click of understanding at the other end. Schumacher compression, zipping quantum states. You learn how to carry more meaning with fewer carriers the day you stop moving letters one by one and start moving patterns. And Schumacher compression is the quantum version of that insight. The discovery that long streams of quantum states can be zipped without losing what matters, provided you treat them in blocks and respect the fragile phase relationships that make them quantum in the first place. Imagine a factory that emits the same kind of qubit over and over, not identically prepared each time, but drawn from a stable recipe. Sometimes this tilt, sometimes that one, with a steady overall fingerprint you could recognize if you looked at thousands together. And now imagine you must store or transmit a long batch with the least number of pristine quantum carriers. The naive way is to keep one qubit for each signal, but that wastes space because most long sequences are not special. They cluster into a small typical set whose shape is dictated by the source's fingerprint, so Schumacher's. Theorem says you can fold the whole block into a much smaller quantum envelope that preserves almost all of the original structure, and then later unfold it with a high chance of perfect recovery, as long as the blocks are large and the source is the same from block to block. The heart of the method is a change in perspective. Rather than asking, what is the state right now, you ask, which part of the gigantic space do typical sequences live in? For a block of length n, that space is unimaginably large, but most of the probability mass lies in a tidy corner, whose size grows like 2 raised to n times a single number. And that number, the source's von Neumann entropy, acts like the per-symbol compression rate. In plainer words, if the source has an entropy of, say, 60% of a qubit per signal, then for very long blocks, you can squeeze almost everything into roughly 60% as many perfect qubits and let the rest ride on ordinary classical bookkeeping without damaging the quantum content you care about. The trick works not by guessing each individual state. Measurement would destroy the very phases you hope to keep, but by performing a gentle, collective operation that maps the entire typical corner into a smaller register while barely touching the geometry inside that corner, the way a well-designed suitcase compresses airspace around clothing without creasing the fabric itself. To feel the difference from ordinary data zipping, notice what you must never do. You must not peek at each system to decide whether to keep or discard it, because peeking in the wrong basis breaks the delicate alignments that later operations rely on. Instead, you apply a global, typical projector that asks a softer question. Does this block look like it came from the usual recipe? And with high probability as the block grows, the answer is yes. Conditioned on that yes, you know the block sits inside a smaller subspace that you can represent with fewer clean qubits. You then use a reversible transformation to pack the state into the smaller register, plus a leftover register that you can safely fix to a standard value. At the end of the line, the decoder inverts the packing step and, with high fidelity, outspills the original block as if nothing had happened. The rare times you land outside the typical region, you pay a small penalty, but that penalty shrinks as you increase the block size, just like the law of large numbers makes coin flip tallies settle near 50-50 over long runs. One of the quiet triumphs of Schumacher's result is that it restores symmetry between the classical and quantum worlds without confusing them. In classical source coding, you exploit repeated patterns to push the average number of bits per symbol down to the source's uncertainty. In quantum source coding, you exploit the shape of the source's long-run fingerprint to push the average number of qubits per signal down to the quantum entropy. But you do it without ever converting the states into letters along the way, because conversion would throw away the continuous alignment information that makes them useful later. The compression is noiseless in the intended sense. The only loss is the vanishingly small chance that a rare atypical block slips through the net, and the bound is tight. You cannot, even with unlimited cleverness, compress below that entropy rate while keeping the freedom to reconstruct with fidelity arbitrarily close to perfect. In the lab, this theory turns into a set of design habits. First, collect signals into blocks so you can act on them together, because the typical subspace only emerges when you look at many at once. Second, learn the source's fingerprint, which is the overall state you would write down if you averaged many emissions. Its own preferred basis hides inside it, and working in that basis lets you pack more gently. Third, avoid work that resolves fine details you don't need, because every resolved detail is a measurement you must later undo, and you can't. Fourth, keep the block coherent from end to end, since a single jolt of uncontrolled noise can push you out of the typical corner and spoil the gain. And fifth, separate quantum burden from classical bookkeeping, using side notes only for things like which slot in your memory currently holds the compressed payload. Side notes you can write and erase freely without disturbing the quantum treasure. Real devices bring practical questions. What if the source drifts slowly over time? What if you do not know its fingerprint ahead of time? What if your hardware cannot perform the full, ideal block operation? And here the field offers universal schemes that learn as they go, estimating the fingerprint on the fly and adjusting the packing transformation in gentle steps. As block sizes grow, the achieved rate slides toward the true entropy without the designer needing a perfect model, much like a smart compressor for music that adapts to genre, tempo, and silence without ever asking the listener to label the track. You also encounter a variation with side information. Suppose a helper holds a correlated quantum memory. If they whisper classical hints to the decoder, you can sometimes compress even further for the same error budget. But the payment must be counted properly. Hints are a resource, and the final rate still traces back to entropic quantities of the joint source, held firmly in place by inequalities that guarantee you never get something for nothing. The boundary between what can be compressed and what must be kept also has a thermodynamic flavor. When you reduce the dimension of the register that holds your information, you create room you can reset for the next batch. But resetting carries a physical cost if you erase classical labels. Quantum compression places that cost where it belongs, on disposable bookkeeping, while preserving the costly, phase-rich part in a tight, coherent parcel. In that sense, Schumacher's theorem is not just about saving memory, it is about locating value. Keep the parts you cannot recreate from public notes, discard the rest. Perhaps the most illuminating way to internalize the idea is to picture a choir singing from a shared score. If you record each singer on a separate track, you fill a hard drive quickly. If you recognize that most of the music lives in a structured harmony, and only small deviations make each performance unique, you can store the performance in a compact form that preserves the chords and timing while compressing the rest. Crucially, you must not first transcribe each voice into sheet music, because the magic lives in the overtones and phase relationships that printed notes miss. Treat the performance as a whole, and you can keep more music with fewer files. Treat it as a pile of isolated notes and you lose the shine. Schumacher compression is the physics version of that wisdom applied to streams of quantum states. And so the promise is clear and practical. If you are building a network of quantum sensors, an archive of fragile states, or a long-distance link that must buffer quantum messages before forwarding them, you don't have to buy one perfect qubit of memory for every signal. You can buy to the entropy, operate in blocks, keep coherence, and reach fidelity targets that would be impossible under one-by-one thinking. It teaches you to see beyond individual letters to the language itself, to recognize that the true burden is the structure you cannot recreate later, and to let the rest ride on classical notes. When you carry that habit forward, you design systems that are lighter, quieter, and truer to the physics, zipping quantum states not by squeezing them into smaller boxes of the same kind, but by folding long stories into compact forms that remember exactly what makes them worth telling again. No cloning and no deleting as theorems. You learn the character of quantum information the moment you try to do the two most ordinary things in the digital world, copy and delete, and discover that nature refuses both in their perfect, universal forms. The no-cloning theorem says you cannot build a device that takes an unknown quantum state and produces two perfect identical copies for every possible input, and the no-deleting theorem says you cannot take two identical copies of an unknown state and erase one of them, leaving the other untouched for every possible input. At first this feels like an annoyance, but as you sit with it, you realize it's a deep teacher, forcing you to see information not as ink you can smear around, but as a carefully choreographed pattern that must be moved, rotated, or hidden without being duplicated or destroyed. Why can't you clone? Because the operations allowed by quantum mechanics are linear and reversible, and those simple words have sharp teeth. A machine that perfectly copies two different states would also have to copy any blend of them. But copying a blend in a linear, reversible world would change the very interference that makes the blend what it is. So the promises you need to keep for the individual states and the promise you need to keep for their blend collide. You can copy orthogonal states, the ones a single yes-no test can always tell apart, because there the promises don't conflict. But you cannot make a universal photocopier that works for all inputs without error. In practice, this means the quantum world protects its secrets at the hardware level. If I send you qubits carrying a code and an eavesdropper tries to copy them en route, their attempt necessarily disturbs the signals in a way you and I can detect later by comparing samples. Why can't you delete? The same logic points back at you from the other side. A machine that takes two identical copies plus a standard blank and returns one copy plus a standard blank would have to act the same way no matter which state you fed it. But if the action is reversible, there is nowhere for the extra copy to have gone, except into some other part of the universe. You haven't truly deleted the information. You have displaced it into the environment, into heat, into some ancilla you didn't look at. So the no-deleting theorem is a mirror that shows you the conservation of quantum information. You can move it, scramble it, hide it, or make it unreadable without a key, but you cannot make it not exist. Pair this with Landauer's lesson that erasing classical records creates heat, and you get a full circle. Even in the best case, cleaning up after yourself has a physical cost. And in the quantum case, cleanup is often just relocation. These theorems are not scolding signs on a lab door. They guide how you actually build things. In quantum error correction, for example, you never clone an unknown qubit to guard it. Instead, you spread its delicate pattern across a larger system using entangling operations so that no single piece holds the whole story. If noise nicks one part, you can heal the pattern by touching several parts together without ever needing a perfect copy. In quantum teleportation, you never copy a state and ship it. You spend shared entanglement and send a small classical message that lets the receiver reconstruct the state while the original is necessarily destroyed. By the very act of learning the message to send, the scheme works not in spite of the no-cloning rule, but because of it. The state is transferred, not duplicated, and the book balancing is enforced by physics, not by our promises. The limits also tell you what is possible. You can make approximate cloners that do their best on average and achieve a known ceiling of fidelity. You can make state-dependent cloners that work very well for a specific, agreed-upon set of states. You can amplify certain signals if you accept added noise. And you can create multiple classical copies of a measurement result once you've measured. but then you've given up the state's phase relationships that powered interference. The lesson is humble and practical. Choose the right notion of copy for your goal, and accept that anything universal must be imperfect. On the deletion side, you can randomize or twirl a state so that what remains is effectively useless without a key, but that key lives somewhere. The no-hiding principle crystallizes this. If information seems to vanish from a system after a reversible process, it must have moved into correlations with something else, and you can in principle retrieve it by gaining access to that something else. Black hole thought experiments drew strength from this idea, but you don't need cosmic stakes to feel its bite. Anytime you push a quantum memory toward a fixed state with a clean, controlled operation, you are planting the missing distinctiveness in an ancilla or the environment. And if you want real forgetting, you pay in heat and irreversibility when you wipe those records. The pair of theorems also explains familiar folk wisdom. Why you cannot secretly peek at a quantum message and leave it pristine. Why you cannot fan out a quantum update across a network the way you fan out a classical update. Why no broadcasting holds even for mixed states that aren't perfectly known. And why entanglement has a monogamy flavor. You can't share maximal quantum alignment with many partners at once, because doing so would amount to spreading precise copies of certain correlations. The algebra behind these statements is tidy, but their human meaning is cleaner. Quantum knowledge is scarce and relational, and when you try to spread it too thin, it evaporates into noise you can only partly control. Day to day, technicians live inside these boundaries. When they design repeaters for long-distance links, they know they cannot simply clone weak signals to boost them, so they chain together entanglement swapping and error correction. When they design secure keys, they exploit the fact that an eavesdropper cannot copy the raw qubits without leaving footprints. When they design memories, they plan for backup, not by cloning the unknown content, but by encoding it across many parts with checks that let them reconstruct after local damage. And when they design reset operations for qubits in a crowded chip, they accept that true forgetting creates heat and that fast. Cold reset requires clever engineering to funnel the discarded information out in controlled ways. If you like to test ideas by pushing them to the edge, try this thought. Suppose you could clone any unknown state. Then you could make many copies, measure each in a different way, and stitch those readings into a complete description that breaks fundamental uncertainty limits. Or suppose you could delete one of two copies. Then you could, in reverse, create a second copy out of nothing by running the machine backward. Both fantasies clash with the same pillars of linear, reversible dynamics. So the theorems are not arbitrary stop signs, but signposts that keep the map consistent. Perhaps the softest way to carry all this is to think of quantum information as a melody rather than a printed lyric. You can transpose it, weave it into a harmony, spread it across instruments so no single microphone captures the whole, and even move it from one hall to another by coordinating players at a distance. But you cannot make perfect, universal duplicates of an unknown performance on command, and you cannot unmake one of two identical performances without that music living on somewhere else. Respect that, and the rules stop feeling like fences and start feeling like rails, guiding you to technologies that work because they cooperate with the grain of reality. Communicating by transferring, protecting by distributing, erasing by relocating and paying the cost, and always remembering that in this world, the most powerful tricks are not about having more copies, but about shaping where and in whom the single true pattern resides. Teleportation. Sending state, not stuff. You begin with a simple picture. Two distant labs agree to hold hands before they speak, not by sending a box across town, but by sharing a quiet connection that lingers even when they're apart. And that connection is entanglement, the strange, resource-like link that lets quantum teleportation move a state from here to there without the stuff ever traveling. The message you carry isn't an object, it's the full way of being of a system, the orientation of its hidden arrow and the choreography of its possibilities. And teleportation is the protocol that transfers that way of being intact while the original is consumed in the process, like moving a flame from one candle to another with a single breath that extinguishes the first at the exact moment the second ignites. The steps are disarmingly concrete. First, you and your partner create a pair of systems in a special joint state and split them. One half stays with you. One half goes to them by any ordinary means before the game begins. Next, when it's time to send the state of some fresh system in your lab, you perform a joint measurement on your local half of the shared pair and the fresh system. A measurement that sorts their combined possibilities into 4 tidy patterns. That act consumes your original state. It cannot survive the test, and produces 2 classical digits of result that you can phone, text, or shout across the room. Finally, your partner uses those 2 digits to choose one of 4 simple fixes on their half of the pair. A small set of flips and twists that align their system into exactly the state you started with. Nothing faster than light has happened, because the last step waits on an ordinary signal and no law has been dodged, because the original was destroyed by the very act that produced the digits needed to complete the transfer. What makes this feel so different from science fiction is that you never copy or peel the state away to inspect it. You prepare a shared resource ahead of time. You perform a particular measurement that entangles and collapses in a controlled way. And you send a small classical message that tells the receiver which finishing move to execute. The distance between labs can be a table's width or many kilometers, limited only by how well you can distribute and preserve the initial entanglement, and how quickly you can deliver the 2 digits. And the reason anyone trusts this is not romance but bookkeeping. The mathematics of the protocol guarantees that, averaged over all possible inputs, the received state matches the original as if it had been carried in a perfect bubble, while any attempt to send the state without shared entanglement would fall far short of that fidelity. In other words, teleportation is not a maybe trick that sometimes works. It is a recipe that, with good components, achieves a benchmark no naive method can pass. In the lab, the pieces are surprisingly varied. With single photons, you can generate entangled pairs in a crystal, send one into a long fiber or through open air to a distant station, and later teleport the state of another photon by combining it with your local half in a special interferometer and detecting a pattern that tells you which digits to send. With trapped ions, you can entangle neighbors with laser pulses, move one ion to a different zone, and teleport states across the chip with high fidelity. With superconducting circuits, you can build microwave entanglement in on-chip resonators and do the same dance at cryogenic temperatures. Each platform wrestles with its own flavor of noise, loss in fibers, scattering in air, crosstalk in chips. But the logic stays the same. Share entanglement, perform the right joint measurement, send 2 ordinary digits, apply the correction, and the distant system now is what your local system was. The catch, and it's a feature, not a flaw, is that you cannot do this without spending the shared link. Each teleportation consumes 1 pair of entangled systems, much like spending a token, and you cannot bypass the ordinary signal that carries the 2 digits, which means you cannot signal faster than light no matter how spooky the setup looks. This cost structure turns teleportation into a kind of currency exchange. You burn 1 unit of entanglement and 2 classical bits to move 1 quantum state. The exchange rate is exact and non-negotiable, and it sits at the heart of many designs for a future quantum internet where entanglement is created, stored briefly, and spent to bridge long distances. Because entanglement is fragile, engineers extend reach with repeaters, intermediate stations that create short links of entanglement, stitch them together by swapping partners, and keep doing so until the shared link spans the full distance. Once the endpoints share a clean pair, teleportation can hop a state across the whole path. Even if the original channel is too lossy to carry the system itself, the same idea lets small quantum processors cooperate. Teleporting a state or even a gate between chips can offload work and sidestep wiring limits. And in error-corrected architectures, teleportation-based methods are a practical way to apply difficult operations using magic helper states distilled elsewhere. If you're wondering how real this is, check the milestones. Researchers have teleported states across lab tables, through city fibers, between mountain stations across free air, and even between ground and satellite links, always respecting the final signal step, and always verifying fidelity above the best classical limit. In chips, teleportation now functions as a routine calibration and connectivity tool. And in networks, trial systems combine entanglement distribution with memory elements so that the link survives the microseconds or milliseconds needed to relay the digits. The protocol also carries honest limitations that shape experiments. The joint measurement that kickstarts teleportation cannot always distinguish all patterns perfectly with linear optics, so photonic demonstrations accept a lower success probability or add auxiliary resources to improve it. Memories that store entanglement long enough to wait for signals must fight decoherence. Corrections must be applied quickly and accurately, and security-minded designs must account for side channels where unwanted light or heat could reveal more than intended. None of these break the idea. They refine it, the way radio engineering turned a principle into dependable devices by taming interference, echo, and drift. Philosophically, teleportation is a quiet lesson in what it means to move information. The state is not a tag glued to a particle, but a set of relationships a system has with the rest of the world. By arranging a specific pattern of relationships, shared entanglement, a joint measurement, a classical message, a correction, you recreate those relationships elsewhere while the old ones are dismantled. So what travels is structure, not substance. That is why the original cannot remain as it was. Leaving it intact would amount to making a perfect copy, which the rules of this world forbid. Instead, the protocol balances the books automatically, guaranteeing that when the new state appears, the old one has ceased to exist in the form that held its secrets. Day to day, the usefulness is practical, not mystical. Teleportation lets you route quantum states around lossy or noisy parts of a setup, connect chips that would otherwise interfere with each other, shift delicate states out of a device for storage or further processing, and execute operations remotely by moving the inputs instead of the tools. It underpins secure tasks because any eavesdropper who tries to intercept the shared link or the classical digits leaves fingerprints the users can detect. And it suggests a blueprint for scaling, where the hard work of creating pure entanglement happens in specialized hardware, and the final users simply spend that resource to move states where they're needed. If you hold the image of the two candles, one dimming as the other brightens, you capture the essence without the equations. Prepare a shared flame in advance. Perform a coordinated move that snuffs your local flame in a way that writes two numbers. Send those numbers on an ordinary wire and watch a distant wick catch light in the same pattern yours had. Nothing solid crossed the gap. Nothing cheated the speed limit. And yet the pattern you cared about arrived exactly where you wanted it, ready to interfere, compute, or be measured as if it had been there all along. That is teleportation's gentle promise. In a world where copying is costly and travel is cruel to fragile states, you can still send the way a system is, faithfully, lawfully, and with good tools, on demand, by spending the right kind of connection and letting structure, not stuff, do the moving. Superdense coding. 2 bits in 1 qubit. You discover a small loophole in your own intuition the day you try to pack more meaning into fewer couriers, and learn that with the right preparation, 1 flying qubit can carry 2 classical bits worth of message, not by breaking physics, but by spending a resource you created earlier. And this is superdense coding, a protocol where you and a partner first manufacture a shared quantum link, keep 1/2 each, and then, when the time comes to speak, you stamp your half with one of 4 tiny, reversible moves and send only that qubit. At the far end, your partner performs a single joint test on the 2 halves and reads out one of 4 unmistakable patterns, recovering 2 bits of message from a single quantum traveler. The trick doesn't cheat any limits, because the extra capacity is prepaid by the entanglement you seeded before communication began, so the 1 qubit flight is only part of the story. The hidden co-ownership of the pair acts like a silent second wire laid in advance, and together the moving qubit plus the standing half can carry 4 clean symbols instead of 2. To feel how this works without equations, imagine you and your friend starting with 2 coins that are secretly rigged to land in perfect step. They will be either both heads or both tails, never mixed, and neither of you knows which until you check. Now, instead of flipping your coin randomly, you perform a precise nudge that changes the relationship between the two coins, leaving the link intact but switching it into one of 4 distinct togetherness styles. You then mail your coin, and your friend, holding both, checks in, a basis that cleanly distinguishes those 4 styles. The result tells them exactly which nudge you used, which you can label 00, 01, 10, 11 to send 2 bits. In the real protocol, the coins are entangled qubits, and the 4 togetherness styles are the famous Bell states, and your nudges are tiny rotations that flip and twist your local half, just enough that the joint pattern hops from one Bell state to another in a controlled way. Crucially, if you hadn't shared entanglement in advance, no single qubit you could send would let your partner distinguish 4 perfectly. At best, they'd tell 2 apart with certainty. So the doubled payload is genuinely about preparation, not about squeezing extra letters into a smaller envelope at the last second. The elegance hides practical conditions. Your partner must be able to perform a measurement that distinguishes all 4 joint patterns reliably. In some hardware, such as linear optics with simple tools, you can only tell 2 out of 4 without extra resources, which turns the protocol into a coin toss of success, unless you add more ingredients like auxiliary photons or special interactions. In trapped ions and superconducting circuits, fully distinguishing the patterns is routine because the qubits can be made to talk strongly. Regardless of platform, you also need shared timing, phase references, and a stable environment so that the delicate link you created earlier survives until the message is sent. If noise partially blurs the link, the set of distinct patterns collapses toward each other, and the recoverable message drops below 2 bits. A reminder that entanglement is not a binary possession, but a resource that comes in degrees and decays with neglect. The accounting side is just as important as the lab side. Superdense coding does not overturn the earlier lesson that a bare qubit line yields at most 1 classical bit per use. Instead, it belongs to entanglement-assisted communication, where you count both the forward quantum uses and the stock of shared pairs. Spend 1 pair and 1 qubit transmission, and you can send 2 bits. Spend 2 pairs and 1 higher dimensional particle, a qubit, and you can send even more because higher dimensional shared links support more than 4 perfectly distinct joint patterns. Conversely, if you ration your pairs, the advantage shrinks, and if you forbid entanglement entirely, you fall back to the usual ceiling. This clarity keeps engineers honest when they compare designs. A spectacular headline rate usually assumes a supply of pre-shared links whose creation and maintenance have their own costs. Links that often must be refreshed via distribution, purification, and storage before the next burst of messages. The protocol's uses are concrete. In a future quantum network, superdense coding can act like header compression for control traffic, letting distant nodes send twice the classical instruction payload through scarce quantum connectors while reserving ordinary fiber or radio for bulk bits. Inside quantum processors, it can move calibration choices or branch signals between chips without tying up 2 physical lines. In hybrid systems that combine quantum memory with classical processing, it can shuttle settings and keys across lossy segments where sending 2 separate qubits would fail, but sending 1 qubit backed by a stored half pair still succeeds. And in certain secure setups, it offers a dial between rate and detectability. An eavesdropper who tampers with the shared pairs or the single traveling qubit inevitably disturbs the joint patterns, raising a flag with statistics users can sample. There is also a pleasing symmetry with teleportation that helps you remember both without mixing them up. Teleportation consumes a shared pair plus 2 classical bits to move a quantum state with no qubits traveling, whereas superdense coding consumes a shared pair plus 1 traveling qubit to move 2 classical bits. One moves state using bits, the other moves bits using state. And both obey the same conservative bookkeeping that forbids free lunch while enabling clever trades when the right stockpiles are in place. In networks, The two show up together with quantum repeaters, where entanglement is created over short spans, swapped to reach long distances, and then spent either to teleport fragile states around obstacles or to pack more classical control into the few quantum shots you can afford across a weak link. Of course, the world resists neat stories. Loss in fibers eats traveling qubits, memories leak over time, and devices drift. To keep 2-bit payloads reliable, you monitor the health of your shared pairs, distill fresh ones from many noisy candidates, and schedule your send windows tightly so the link hasn't wilted. You also choose alphabets that match your hardware. On-chip platforms might use microwave photons and tune pulses to hop among joint patterns. Free space links might pick time bin or polarization patterns that survive turbulence, and ion chains might couple motion and spin to make the joint test fast and clean. Each choice changes the error model and the best coding on top, but the core remains the same. A prior link lets one traveler speak 2 clean bits. Perhaps the deepest lesson is psychological. Superdense coding asks you to stop seeing information as a property of the messenger alone and start seeing it as a property of relationships prepared in advance. The qubit you launch carries 2 bits because the world has already been arranged so that 2 hands, reunited, can perform a test that has 4 crisp answers. That arrangement takes effort and is fragile, but when you honor it, the path widens. And if you zoom out, you notice that much of modern communication is exactly this kind of choreography. Caches, codes, synchronization, all ways of paying up front to move more later. Quantum mechanics simply makes the choreography literal. Prepare a shared pattern, apply a tiny local stamp to choose among 4 possibilities, send a single traveler, read the joint pattern, and collect 2 bits where your intuition swore you could only get 1. No rules broken, no free energy conjured, just a new way to think about bandwidth in a world where structure, once prepared and protected, lets small signals speak in larger voices. Entanglement distillation, purifying the precious. You don't start by building a perfect bridge. You start by laying many shaky planks and learning how to keep only the best. And that is the spirit of entanglement distillation, the craft of turning a pile of weak, noisy quantum links into a smaller stash of clean, strong ones using only local operations and ordinary conversation. Imagine you and a partner at distant labs receive a steady drizzle of imperfectly entangled pairs from a fickle channel. Fibers that lose photons, free air that jitters, hardware that drifts. And your goal is not to admire what you have, but to purify it. To use several flawed pairs as raw material and, by coordinating simple moves and sharing the outcomes by phone or fiber, concentrate their togetherness into a few pairs that behave almost like the pristine resource you ordered at the start. The key promise is that you never need to bring the qubits together physically or perform exotic global tricks. Each lab acts locally, comparing notes about what they saw, and decides which pairs to keep, which to discard, and which to mash together so that the good correlations add and the bad ones cancel. A basic round feels like a cooperative game with 2 moves. First, you standardize your messy pairs so they all look similar from the outside, randomizing certain details to turn complicated error patterns into simple ones you can reason about. And then you perform matched operations on 2 pairs at once, like applying the same controlled flip in both labs and measuring one pair as a check on the other. When both of you see matching parity, a sign that errors likely hit in the same way, you keep the unmeasured pair because the procedure has boosted its fidelity. When your notes disagree, you throw that attempt away. It sounds wasteful until you remember what you're buying. With each successful round, the surviving pair becomes more sharply entangled, and by repeating the routine across many inputs, you trade quantity for quality in a controlled, predictable way. Different recipes tune this trade-off. Recurrence protocols are the workhorses when your inputs are quite noisy, boosting fidelity step by step with 2-way communication and a modest yield, while hashing-style protocols act like large-scale laundry, processing big batches at once and keeping a constant fraction when your inputs are already decent. For pure but partially entangled inputs, there's a sibling task called concentration, which extracts almost the maximum number of perfect pairs per batch by reorganizing the existing order rather than fighting noise. A reminder that not all weakness is the same. Some comes from mixing with the environment, some from uneven sharing between partners. In practice, you pick the tool that matches your fuel. The reason you can ever get ahead is that useful correlations tend to line up, while noise tends to scatter. Local checks expose where the alignment survived, and those are the branches you prune toward. Even better, the operations that help against one error type can be alternated to fight another. So alternating parity checks in two complementary ways gradually scrubs both common kinds of flips. If you squint, you see parallels to privacy amplification in cryptography. Many flawed bits plus public discussion can yield fewer secret bits, and in the quantum case, many flawed pairs plus public discussion can yield fewer high-quality entangled pairs. Both trades pay a price in rate to buy a guarantee in quality. Distillation sits at the heart of long-distance quantum networking because raw entanglement is fragile over kilometers. Repeaters break a long span into short links, create entanglement on each short hop, and then do two crucial chores before moving on. They purify each hop to raise its quality, and they swap entanglement hop by hop, so the ends become linked. Without purification, swapping would spread the noise and the connection would die as you added hops. With it, you walk a narrow ridge where each step forward is matched by a tune-up that keeps the link worth having. This is why repeater designs always include memory elements to hold intermediate pairs while checks and phone calls finish, and why the throughput of a network depends as much on distillation yield and memory lifetimes as on the brightness of the sources. In the lab, details matter, and the map is not the territory. With photons, you often start by heralding the rare moments when both sides received something. Then you twirl by shuffling polarizations or time bins. Then you perform bilateral operations with beam splitters and detectors that act like parity meters. With ions or superconducting qubits, you can implement the same logic as deterministic gate sequences and measurements. Across platforms, drifts in phase or timing can quietly undo your gains, so experiments weave in calibration pulses and reference frames to keep the two labs aligned. And because every test risks adding noise, good protocols minimize the number of times you touch each pair before you decide its fate. Distillation is also an honesty machine. It refuses to conjure perfection from nothing, and it sets thresholds. Below a certain starting quality, the routine cannot climb uphill, so part of the engineer's job is preparation. Tame the channel enough that you land above threshold, then let distillation earn its keep. Another part is accounting. Track how many raw pairs you spend per purified pair, how long memories must wait, how dark counts and leakage skew your decisions, and how often you should switch between boosting and swapping to keep the pipeline flowing. When done right, you can watch a noisy curve of correlations bend upward through successive rounds until it clears the bar that your application demands. Teleporting a delicate state, executing a remote gate, or generating a key whose secrecy is certified by the very inability of an eavesdropper to copy without leaving scars. Hidden in all this is a philosophical line worth tracing with your finger. Entanglement, unlike a beam of light or a file on a drive, is not a thing you store in one location. It's a relationship spread across places, and distillation is the act of curating that relationship, testing it, pruning it, and condensing it, so that what remains is not just some correlation, but the kind that cannot be explained by shared history alone. When your checks pass, you have less but better togetherness. A sharper promise that operations performed here will sing in tune with outcomes there. When they fail, you learn to let go and try again, because holding on to weak links only drags the whole chain down. If you carry one actionable picture forward, let it be this. Treat entanglement like a precious metal powdered into sand by a rough journey. You swirl many handfuls in a pan, use simple moves and a steady rhythm to make the flecks settle while the silt washes away, then collect the nugget that remains. The pan is your local gates and measurements. The water is your classical conversation. The rhythm is your protocol's rounds. And the nugget is a purified pair whose value you can spend on the next stage, teleporting a state, packing 2 bits into one traveler, or linking 2 distant processors as if they shared a desk. Nothing mystical, nothing free, just careful work that turns a messy resource into a dependable one, and in doing so makes a sprawling, lossy world feel a little more connected. Error correction, Shor, Steane, surface code. You only understand how fragile a quantum computer really is when you try to make it tell the truth for longer than a blink. And error correction is the art of doing exactly that, catching tiny slips without looking so hard that you destroy the very state you meant to protect. So think of it as building a choir that can sing one note perfectly, even if a few voices go off key, because you never ask a single singer whether they're right. You ask the group for syndromes, little yes-no harmonies that reveal where mistakes happened without revealing the secret melody itself. The first landmark, Shor's code, shows the blueprint in full. Take one delicate qubit and spread its pattern across 9 physical ones, first making 3 voice clusters that protect against flips like 0.1, then weaving those clusters so that quiet phase slips, the kind that rotate the hidden arrow without changing the measured digit, are also caught. You never measure the protected note directly, you measure cross-checks that say, these 2 agree, or this trio hums together, and from that pattern you infer which qubit likely strayed and gently nudge it back. Shor's idea is bold because it proves the principle end-to-end. If you detect errors often enough and repair them softly, you can push the time your logical qubit stays honest far beyond the natural lifetime of any part, and you can do it without ever cloning or peeking at the melody you're guarding. A few years later, Steane's code refined the craft with 7 physical qubits instead of 9, borrowing discipline from classical communication. The same parity checks that catch typos in Hamming's famous scheme become quantum-friendly when arranged, so that flip-type and phase-type errors are handled by twin families of checks that never tread on each other's toes. In practice, you prepare small helper qubits, ancillas, in tidy patterns. Let them listen to selected subsets of your data through gentle interactions, and then read only the helpers. Their pattern of clicks is the syndrome, a compact map from which a decoder decides what to fix. Because Steane's checks are balanced and structured, you can prepare those helpers cleanly and even inject certain states you'll need for computation later. Which is why this code still serves as a teaching lab for fault-tolerant tricks decades after its debut. It teaches another human lesson too. Efficiency matters, and symmetry buys you both clarity in analysis and cleanliness in hardware. Then comes the surface code, the workhorse of today's roadmaps, whose genius is geographical rather than algebraic. Lay your qubits out on a flat grid so that each one talks only to its neighbors. No spaghetti wiring, no long-range gymnastics, and assign tiny square plaquettes to act as neighborhood referees. Some referees check that nearby qubits agree on a parity of flips. Others check a parity of phases, and every few microseconds the grid reports a new snapshot of which squares are upset. A single upset square doesn't tell you much, but the pattern of upset squares across space and time sketches the tracks of errors the way fresh snow reveals the path of a fox. A classical decoder then connects these tracks, often by matching pairs of upset squares into likely paths, and prescribes minimal fixes. Because all checks are local and identical, the surface code tolerates a messy, scalable factory. Add more tiles and, as long as each tile is reasonably good, the protection of the whole improves, much like building a thicker wall from the same bricks. This locality is gold in the lab, where qubits prefer a limited number of neighbors and crosstalk grows with complexity. None of this works if the doctor makes you sicker than the disease. So syndrome extraction has to be careful. Helper qubits must be prepared cleanly, touched to the data in a set order to avoid spreading a single fault, and measured fast. Because measurements themselves can lie, you repeat rounds and look for changes over time rather than trusting one snapshot. Because gates can fail, you design the schedule so that one slip cannot cascade into many. This constraint births the whole field of fault-tolerant design, where every move is chosen so that the worst case still remains fixable. At a practical level, labs now run real-time control loops that prepare helpers, perform check circuits, record the outcomes, and feed them to decoders that update their best guess of the hidden state many times a second, with corrections applied virtually by reinterpreting future operations, or physically by small nudges, depending on platform. The costs are honest. You trade hardware for honesty, wrapping one logical qubit in dozens to thousands of physical ones, and you pay in time by spending cycles on checks instead of pure computation. Yet that trade unlocks something radical, a regime where making the device a little better buys you exponentially more reliability as you scale the code's distance, so long as you stay above a quality line. Early demonstrations have already shown prolonged lifetimes of encoded information, detection of both flip and phase errors in real chips, and first baby steps of computing inside the protected space. Different platforms lean on different virtues. Superconducting circuits push fast rounds and friendly layouts for surface codes. Trapped ions excel at clean, high-fidelity gates that favor Steane-like checks and flexible geometries. Neutral atoms and photonics explore modular variants whose locality maps onto their strengths. Across all of them, you see the same choreography. Prepare helpers, dance the checks, read syndromes, decode, and correct, repeated like a heartbeat. What do these three codes teach you beyond their individual blueprints? First, that protection is pattern management. You never ask for the secret itself. You ask for the shadows it casts when something's wrong. Second, that geometry is destiny. Abstract algebra blooms into hardware reality when your checks align with what your devices do well. And third, that reliability is earned in layers. Shor proves the concept by brute force. Steane trims and balances it with structure, and the surface code industrializes it with local, repeatable tiles that can in principle blanket a wafer or a plane of trapped ions. If you hold one image as you leave, let it be a quilt stitched from many squares. Each square is a small agreement among neighbors. Each stitch is a check that keeps tears from spreading, and the warmth you feel at scale doesn't come from any one patch being perfect, but from the discipline of checking, mending, and layering so that small drafts never grow into a chill. Quantum error correction is that quilt for fragile states, patient, local, and relentless, turning a technology that forgets in microseconds into one that can, with enough care, remember long enough to matter. Fault tolerance, thresholds, and overheads. You don't feel the weight of a quantum computer until you try to make every step safe even when pieces stumble. And that is what fault tolerance really is. A promise that, below a certain threshold of physical error, you can stretch reliability as far as you're willing to pay an overhead. More qubits, more checks, more time, so long as you follow strict rules about how you touch, measure, and compute. Imagine hiking a ridge in fog where every so often you plant a flag, an error check, and as long as each short stride is less slippery than a known limit, you can lay flags closer together, build handrails and make the journey arbitrarily safe. But if the ground is slicker than that limit, no amount of flags will save you. You slide off eventually. That turning point is the threshold. And staying under it is only the beginning, because then comes the budget. How much extra gear you must carry to push your risk down to the tiny level your application demands. The threshold theorem says that if each elementary operation, preparing a qubit, applying a gate, idling, measuring, fails less often than a code-specific number, then by encoding your information and correcting continually, you can make the logical error per step shrink exponentially as you increase the code's size or distance. But this abstract comfort hides a maze of details. The threshold you quote depends on the noise you truly have. Is it mainly bit flips, mainly phase slips, or a biased mix? On whether errors arrive independently or in bursts, on whether faults in control electronics sneak in as patterns that codes expect, or as oddball failures that codes hate, and on how you extract syndromes. Because the act of checking can itself spread a single fault into many, if scheduled carelessly. In practice, you see families of thresholds. A generous one that assumes your checks themselves are perfect, a stricter, circuit-level one that counts every wire and interaction, and hardware-specific thresholds that fall once you factor in crosstalk, leakage to states outside the code space, and slow drifts that mimic correlation over time. Overhead begins with space. To protect one logical qubit, you may need dozens to thousands of physical qubits, depending on the code and the target error rate. A modest demo that just keeps time might make do with a few dozen, while a computation that runs millions of steps without a single logical slip may demand city blocks of hardware. Then comes time. Each round of checks takes a handful of gate layers and measurements, and you must repeat them over and over, feeding their outcomes into a decoder that decides what to correct. If the decoder is slow, you either buffer results, which costs memory and risks backlogs, or accept latency that stretches your logical clock. Modern systems use real-time controllers that update a poly frame on the fly so that many corrections can be applied virtually by reinterpreting future operations rather than physically nudging. Qubits, saving precious nanoseconds. But the bookkeeping and verification still consume cycles. Not all overheads look like qubits in time. Some are factories. To run a universal algorithm, you usually need special, hard-to-make resource states, often called magic states, to implement the few gates your code won't allow you to do cleanly. Producing these states with very high fidelity requires distillation, which eats area and time in bulk, like an industrial plant beside the main city. Route too few resources to the plant, and your program waits on ingredients. Route too many and your chip fills with warehouses instead of workshops. Balancing that area-time volume is a core art of architecture, and it often dominates the total cost more than the data registers themselves. Geometry shapes overhead as much as algebra. Codes that live on a 2D grid with only nearest neighbor interactions, like the surface code, offer comfortable thresholds around the percent level for common noise models and scale cleanly by adding tiles. But they pay with large footprints for certain gates. Alternatives like color codes promise lighter circuits for some operations, but tolerate lower noise or demand more complex layouts. Concatenated codes stack layers of small codes inside each other, giving clean mathematics and flexible gates at the price of wiring and control complexity. Bosonic codes put more of the burden inside a single physical mode. CAT codes, GKP codes, cutting qubit counts dramatically if you can stabilize exotic states, but shifting overhead into precision control and continuous calibration. There is no free lunch, only menus with different prices. The rules of fault tolerance constrain how you compute. You favor gates that don't let one fault blossom into a multi-qubit disaster. You stage measurements so that any single bad outcome can be recognized and contained. And you accept that some elegant gates are banned outright by deep theorems. No code lets you do every logical gate transversely on the same encoding. Workarounds like lattice surgery, code switching, and teleporting gates in from factories become the civil engineering of the field, rerouting traffic to keep accidents small. Noise bias invites cunning. If your hardware makes phase slips 10 times more likely than bit flips, you pick checks that lean into that asymmetry and buy better thresholds for the same parts. If your hardware leaks into unwanted levels, you add leakage removal cycles that pump the strays back down before they unspool damage. If your noise clusters in time or space, you upgrade decoders from simple matching to ones that read tracks across several rounds, using temporal patterns to separate crackling from melody. Decoding itself is a hidden mountain in the overhead landscape. The algorithm that converts a flutter of parity outcomes into a best guess repair must be fast, accurate, and kind to your processor. Match 2 defect points and you guess a short error path. Match thousands over many rounds and you need smarter heuristics, hardware accelerators, or neural aids. A decoder that lags by milliseconds on a system that ticks in microseconds forces you to store corrections or accept stale decisions. Both kinds of overhead. This is why groups prototype decoders on FPGAs, ASICs, and even embedded GPUs, and why the boundary between quantum and classical hardware is itself an optimization problem. Move too much work off-chip and cables. Heat loads and latency become your enemy. Move too much on-chip and you choke precious cryogenic budgets. Threshold is not only a number, it's a discipline. You characterize your devices honestly, including rare events. You tune schedules that keep fragile checks from colliding. You budget for calibration overhead that holds parameters inside their safe lanes, and you monitor for drift, so the real system never wanders above the line. Factories are scheduled like airlines with buffers and reroutes for bad weather. Memories are sized to survive the longest expected delays. And the whole machine is designed around the reality that failure probabilities multiply with depth. So you push error-prone steps earlier, convert physical corrections into virtual ones, and restructure algorithms to minimize the types of gates your code finds awkward. The rewards for doing all this are not theoretical. Encoded qubits now outlive their unencoded parts by clear margins. Round-by-round detection of both main error types runs reliably on chips and in ion chains. First, fault-tolerant logical gates have been demonstrated with checks guarding every step, and small patches of surface code have been stitched and measured like quilts, with decoders steering them safely. Each step down this road looks incremental, but together they add up to a regime, where making components a bit better buys you exponential improvements at the logical level, a compounding effect that turns today's fragile prototypes into tomorrow's dependable engines. Still, honesty keeps ambition grounded. Even with friendly thresholds, overheads for truly large jobs are heavy, often demanding millions of physical qubits plus robust factories and fast decoders. That cost pushes innovation in every direction. Hardware that natively suppresses the most common errors, codes that exploit bias to cut qubit counts, bosonic encodings that pack more protection into fewer elements, and algorithms that reduce the number of costly gates you need. The destination is not a single magic number, but an ecosystem where thresholds are respected, overheads are engineered, and performance goals are met by matching the right code, the right architecture, and the right workload. If you want a single image to hold on to, picture a suspension bridge across a windy channel. The threshold is the maximum gust the cables and towers can handle safely. The overhead is the extra steel, the redundant strands, the dampers, the frequent inspections, and the traffic rules. Build below the gust limit and add enough structure, and the bridge stands for decades. Ignore the limit or skimp on redundancy, and the first storm will tell you. Quantum fault tolerance is that same bargain in a different medium. Respect the line, pay the overhead, and you can carry delicate computation across a noisy world as far as you dare. Stabilizer formalism, made intuitive. You understand the stabilizer way of thinking the moment you stop describing a quantum state by what it is and start describing it by what it obeys, not by a long coordinate list, but by a short set of calm rules that the state leaves unchanged, like a melody defined by the harmonies that never budge, no matter how often you play them. In practice, those rules are simple. Commuting checks built from the basic flips and phase flips we use to poke qubits. And a stabilizer state is any state that answers unchanged to each check on the list, while anything that answers flipped is flagged as out of tune. Suddenly, a sprawling cloud of amplitudes collapses into a tidy notebook. Write down a handful of generators, independent rules that don't argue with each other, and you have specified an entire subspace of allowed states, because any other rule you care about follows from combinations of the ones you listed. The number of independent rules tells you how tightly you have fenced things in. With more rules, you shrink the space of possibilities. With fewer rules, you leave more freedom. So a code space becomes the set of states that keep these particular harmonies intact. And a single well-defined state appears when your rules are numerous enough to pin everything down. This viewpoint immediately explains why parity checks in quantum error correction don't reveal the secret melody. When you measure a stabilizer, you are asking whether the current state still obeys a chosen rule. A healthy system says yes and remains unchanged, while a nudge from noise might flip the answer to no, telling you a fault passed by without forcing you to crack open the hidden pattern. Even better, different error types have different fingerprints relative to the rules. Some faults commute with a check and pass silently. Others anti-commute and flip the sign. So a brief pattern of yes-no across many checks becomes a syndrome that points to likely culprits. This is why the formalism feels so natural for codes. Instead of tracking every amplitude, you track which rules still hold, and the rest of the recovery problem becomes a tidy puzzle of reconciling the broken ones with the smallest fixes. The stabilizer lens also reveals an unexpected simplicity in certain quantum circuits. There is a family of operations, the Clifford family, that takes basic flips and phase flips to new combinations of the same, like shuffling chords in music without ever leaving the key. Because these operations never turn a simple check into something exotic, stabilizer states pushed through these circuits remain stabilizer states, and you can update the rulebook directly without touching amplitudes at all. This is the core of the famous simulation shortcut. If your computation begins in a stabilizer state, uses only Clifford gates, and measures in compatible ways, then a laptop can track the evolving rules efficiently using a compact tableau. No heavy wave function math needed, because you only ever record which checks become which. That efficiency does not make the quantum device useless. It makes the structure crystal clear. We can separate what brings genuine quantum hardness, those rare gates that leave the stabilizer world, from what merely rearranges rules in a space we understand perfectly. With this in mind, you can reread many ideas through a friendlier grammar. A cluster state in measurement-based. Computing is simply a graph whose edges encode pairwise. Rules, multiply any two neighboring rules and you get a new one that links a wider patch. So long. Strings of adaptive measurements become a controlled way to rewrite the rulebook until the remaining qubits hold the answer. Graph states used in networks are stabilizer states too, which is why local tests on small neighborhoods certify the health of a large distributed resource without a global peak. Even entanglement structure becomes a matter of bookkeeping. If the rulebook for the whole can't be written as a union of separate rulebooks for the parts, you know, the togetherness isn't explainable by shared history alone. And because the rules are built from the same elementary pokes that noise uses, you can watch faults propagate through a circuit just by updating which checks they flip. No mystery. Only arrows on a diagram that a decoder later stitches into likely paths. Where earlier topics spoke of specific codes, here the stabilizer formalism steps back and hands you the drafting tools. You choose generators that match your hardware's strengths. Local ones for grids, balanced ones for symmetric layouts, biased ones if your device trips in one direction more than the other, and you ensure they commute so that measuring them in any order never creates fresh trouble. You design helper routines that couple ancillars to the data in patterns that read the rules, yet avoid spreading a single bad ancillar into many broken rules. You keep a frame of pending sign flips, never rushing to physically fix everything, by updating the rulebook and letting future gates account for the changes, which saves time and reduces risk. And when you must step beyond the safe family of rule-preserving gates to achieve universality, you do it knowingly. You inject a specially prepared non-stabilizer resource and then teleport its influence into the encoded space using only rule-respecting moves, so that the dangerous part never touches the data directly. In effect, the stabilizer world becomes the highway, and the scarce non-stabilizer resources become toll passes you insert only at designed junctions. The beauty of living by rules rather than coordinates is scale. Add more qubits and the naive description explodes, but the rulebook grows only linearly with the number of generators, so large states remain graspable. Commissioning a new device becomes an exercise in learning, which checks you can measure reliably and how quickly you can cycle them. Troubleshooting becomes a matter of comparing the observed yes-no patterns to the tidy expectations of the rulebook, and optimization becomes a game of choosing generators whose graph minimizes crosstalk and maximizes tolerance to the specific noise your lab fights most. Even the philosophy is refreshing. In classical life, we describe objects by attributes they possess, but the stabilizer view asks you to define quantum states by symmetries they preserve. Certainty is encoded not as an inner label, but as a portfolio of invariances. You can test locally without destroying the whole. Errors are not sins, but mismatches with those invariances. And correction is not guesswork, but the gentle reassertion of rules that were always meant to hold. If you carry one memory from this tour, make it this. The stabilizer formalism is the quiet librarian of quantum information, filing vast stories under a small set of headings and letting you find what you need without opening every page. It turns syndrome extraction into non-invasive queries, turns certain gates into line edits on the rulebook, and turns the sprawling geometry of many qubit space into a clean map of neighborhoods and streets. And when you eventually do step outside the library to run a gate that the rules cannot absorb, you know exactly what you are spending and why, which is the essence of control. Fewer surprises, more design, and a clearer path from fragile physics to reliable computation. CSS codes and topological protection. You learn the secret of CSS codes the moment you realize you can split the job of protection into two clean chores, one that watches for flips of the digit and another that watches for slips of the fissure, and let each chore be managed by its own familiar classical code. Calderbank Shor Steane codes are built like that on purpose. Start from two ordinary error-correcting codes that catch different kinds of typos, weave them together so their parity checks never step on each other. And you get a quantum code whose tests naturally fall into two families. One sensitive to things that change the visible value, and one sensitive to things that only twist the hidden alignment. The beauty is that you can design each family with all the intuition you already have from classical coding. Low-weight checks to keep measurements gentle, sparse graphs to localize faults, large distances to push rare failures far away. Then overlay them with a single consistency rule so that every test in one family stays blind to the corrections being staged by the other. In practice, a CSS code is a tidy rulebook with two columns of checks, and extracting a syndrome means preparing small helper qubits to listen to a handful of data qubits for one column at a time, recording yes/no answers that never reveal the protected information itself. When you look at Steane's 7-qubit code through this lens, you see its classical spine. One set of checks comes straight from a Hamming code's parity. The twin set is its mirror, and together they catch both types of quantum slips with a minimal footprint. Proof that quantum structure doesn't have to feel alien if you start from patterns you already trust. The magic begins to feel physical when you lay a CSS code out on a lattice and realize that the two columns of checks can be made local. Each test touches only nearby neighbors, so faults don't spread far, and then something deeper appears. The code's protected information stops feeling like a number stored at one spot and starts feeling like a global feature of the whole fabric. This is the doorway to topological protection, where the logical degrees of freedom are not small labels inside a device, but large-scale patterns that cannot be changed by any short, clumsy nudge. Picture a quilt that wraps around into a loop so it has no edge. And imagine two kinds of stitches you can check on each square. One ensures that the values around a vertex agree in a certain way. The other ensures that the values around a face agree in another way. If a local error pops a stitch here or there, your checks flag a pair of small defects you can trace and repair. But to actually flip the encoded information, you would have to drag a thread all the way across the quilt and join it back to itself, an operation so long and unlikely under local noise that its risk falls rapidly as you make the quilt larger. In the language of geometry, your logical operations are extended paths that wind around holes, and two paths are considered the same if one can be deformed into the other without crossing a stitch. So what you're storing is not a bit in a box, but a class of shapes in a surface, a kind of memory that lives in how it wraps, not where it sits. This topological viewpoint does more than sound poetic. It changes engineering choices. When your checks are local and uniform, you can tile them across a chip or an array of trapped atoms without spaghetti wiring. When your logical operators are long paths, you can visualize distance, the minimum length of a damaging path, as straight geometry and tune it by changing the layout, adding boundaries or carving holes that act like vaults to park extra logical qubits. When an error creates two neighboring defects, you can treat decoding like solving a maze, pair up defects by plausible short routes, and cancel them with minimal surgery, while long conspiracies that could change the code's meaning are exponentially rare at modest physical error rates. And when your device has a strong bias, say, phase errors are far more frequent than flip errors, you can tilt the CSS construction itself, giving one column of checks heavier armor than the other, so you buy more protection where reality actually hurts, cutting overhead without asking for cleaner parts. The CSS recipe scales beyond square quilts. Modern quantum LDPC designs keep checks sparse, and weights low while letting the number of qubits grow, borrowing blueprints from expander graphs and product constructions so that you can keep both columns thin and still drive distances sky high. Here the same two-column logic rules. One family of checks watches one error type. The other family watches the complement. But now the incidence pattern is chosen for strong expansion, which means local noise has a hard time hiding in unlucky clusters. You get codes with constant weight checks, constant rate, so you don't drown in overhead as you scale, and distances that grow with the system size. An appealing trio for machines that must juggle millions of elements. And because the checks remain CSS style, syndrome extraction stays modular. You can route helper qubits in neat, repeated patterns, schedule the two families in interleaved rounds, and feed the results to decoders that exploit the graph structure, from belief propagation to newer combinatorial methods that read error footprints across time. Topology also gives you control knobs that feel architectural rather than abstract. Introduce boundaries of two types and you can create and annihilate defects in controlled ways, which lets you perform logical operations by moving and merging regions of the code's fabric, sometimes called surgery, rather than applying delicate global gates. Add a hole and you mint a new place to store information. Slide a hole around another and you enact a non-trivial transformation on the logical state without ever touching it directly. In more exotic settings, braiding long-lived quasi-particles in materials with a natural gap accomplishes the same logic in hardware, making the computation live in paths rather than pulses, though that route leans on condensed matter feats still under active development. The shared message is that shape is protection. When your data is the shape, local errors can't quietly rewrite it. They only tug at the fabric, leaving tracks your checks can see and your decoder can mend. None of this is free, and the trade-offs are honest. Local CSS codes tend to require many physical qubits per logical one to reach very low error rates, and the price of long distance is a wide footprint and frequent measurements. Matching decoders must keep up in real time so that small clouds of defects don't harden into long paths while you think. Fabrication must deliver uniform couplings, so the neat geometry isn't undercut by hotspots of failure. And code design must balance check weight, too heavy spreads faults, against sparsity, too light leaves blind spots. But the payoff is structural. You get protection that improves predictably as you scale. You get modular tiles that manufacturing can copy-paste. And you get a visual, testable story for why the memory holds. The kind of story that survives contact with heat leaks, drift, and crowded chips. Perhaps the most helpful intuition to carry out of this is that CSS codes are a division of labor turned into a geometry. Instead of asking one complicated test to do everything, you ask two simple, compatible test families to do their halves. And then you lay them out so the thing you care about becomes a global property of the layout itself. In that world, reliability is not a promise whispered into a single fragile element, but a pattern that must be changed across the whole by a coordinated push. Something nature's random jostling is very bad at. So when you hear CSS codes and topological protection, picture a fabric with two kinds of stitches, local hands checking each square, and messages stored not in ink but in the way the threads wind around empty space. Make the fabric bigger and the message hardens. Measure steadily and small snags vanish before they spread. And when you finally need to compute, you don't pry open the memory. You reshape the fabric in ways your rules allow, letting geometry, not guesswork, carry you from fragile parts to dependable outcomes. Magic states, fuel for universality. You realize a quantum computer is missing a spark the day you learn that a large class of its moves, precise, orderly, wonderfully simulable, can be tracked by an ordinary computer if that's all it ever does, and that the spark which makes the machine truly open-ended comes from special states prepared off to the side and fed in like fuel. These are magic states, and their job is simple to say and hard to supply. They let you perform at least one operation that sits outside the easy, neatly structured family of gates, so that your computation is no longer confined to motions a laptop can mimic efficiently. Picture a workshop where every tool but one is safe and predictable, good for shaping, but never for creating new kinds of shapes. Magic states are the raw materials you bring in that, when pressed through a standard jig, allow that one risky, transformative cut you couldn't otherwise make. Operationally, you factory prepare identical copies of a certain single qubit or small multi-qubit state with extra twist in its geometry. Then you couple one of those copies to your encoded data through a short, well-behaved circuit, measure a helper, and, depending on a 2-bit outcome, either get the desired exotic gate for free or apply a tiny correction to finish the job. The delicate part is that those helper states must be very clean, because any noise that sneaks in when you feed them to your data does not just blur the computation, it can become the dominant source of errors in the entire algorithm. As a result, most blueprints devote real estate and time to distillation, a staged purification process that starts with many rough magic states and winnows them down to fewer, sharper ones by running small, fault-tolerant subroutines and checking parities that catch imperfections. Each round consumes a batch, tosses the ones that fail consistency tests, and outputs a smaller set with higher fidelity. And by stacking rounds like sieves, you can reach the quality your application demands, at the price of space and patience. Why do these states deserve the name magic? Because they carry a kind of non-classical resource that your tidy gates cannot create on their own. If you represent quantum states by quasi-probability charts, the friendly, easily simulated world corresponds to charts with all non-negative entries, while magic states exhibit negativity, not a moral judgment, but a signature that no ordinary random process can imitate. Under operations that keep you inside the easy family, this negativity cannot increase, so you cannot conjure magic from thin air with safe moves alone. In that sense, magic behaves like energy for a forbidden engine. You can move it around, concentrate it, burn it, but to get more, you must pay with raw ingredients. Researchers quantify this with magic monotones, numbers that go up or down predictably as you process states, giving you accounting rules that help design protocols and lower bounds that no wishful thinking can beat. This resource view is not philosophy for its own sake. It tells you why certain subroutines are necessary, how many raw copies you must budget for a given error target, and which factory designs give the best fidelity per input. The most famous species is aligned with the so-called T-type operation, a gentle twist that, when added to your safe toolkit, completes the set you need for universal algorithms. But the ecosystem is larger, different hardware favors, different resource states, and some platforms target operations akin to controlled flips, or small rotations around odd axes, each with its own family of distillation routines. When noise has a bias, say, phase mistakes are common while bit flips are rare, you can exploit that bias by choosing magic states and sieves tuned to the real error landscape, cutting overhead without asking the impossible from your qubits. When connectivity is limited, you pick factory layouts that keep interactions local, moving distilled states toward the data region by short, repeatable hops rather than global shuffles. When measurement is fast but gates are slower, you lean into injection methods that trade extra readouts for fewer risky pulses. And when your cryogenic controllers are bandwidth limited, you schedule factories like airlines, staggering departures so that fresh fuel arrives just in time for the hungry parts of the algorithm. There are also deeper tricks that stretch the budget. Catalysis, where a high-quality magic state helps transform several rough inputs into better outputs while returning to its original form, acts like a reusable mold that doesn't wear out quickly. Compression, where you pack the needed magic for a batch of gates into fewer carriers by choreographing how you inject and correct, reduces the number of times you touch the data. And routing via code switching, where you momentarily park your logical qubits in an encoding that makes a particular exotic gate cheap before switching back, can move cost from rare heavy lifts into more frequent, lighter motions. Your hardware performs well. All of these are honest trades. No protocol makes magic for free, but they show how architectural choices can convert a daunting headline cost into a workable pipeline. From the vantage of security and verification, magic states sharpen your attention. Because they sit outside the easy family, they are tempting attack points and fragile to calibration drift. Practical systems therefore include witness tests that sample a fraction of produced states and check simple inequalities that non-magical imposters cannot pass. They also practice interleaved benchmarking, weaving magic injection steps into known sequences so that any slow degradation or phase creep becomes visible in statistics. And in distributed settings, say, a small processor calling on a remote factory over a network, protocols exist to certify that what arrived has the right kind of non-classicality, even when you distrust the producer, a step toward cloud services, where the most expensive part of universality is outsourced but still auditable. Day to day, the presence of factories reshapes software too. Compilers track not only the count of exotic gates, but their pattern in time and space, clustering them to amortize overhead, replacing some with cheaper gate identities discovered by algebraic rewriting, and rearranging arithmetic so that the peaks in magic demand line up with the conveyor belts from the factories. Algorithm designers chase formulations with fewer of these costly steps, turning, for instance, long chains of small rotations into additive phases that can be accumulated by cheaper means. And hardware teams co-design pulse sequences that make injections smoother and less sensitive to crosstalk. In aggregate, these choices turn a brute force plan that would drown in factory traffic into a viable campaign where the expensive resource is consumed steadily, not in disruptive spikes. Perhaps the most clarifying way to carry this idea is to think of magic states as tickets for non-trivial transformations. Your machine can rehearse, rearrange, and stabilize a vast chorus of easy moves forever. But whenever the score asks for a passage that cannot be rendered in that language, you must spend one ticket per bar. The tickets are minted from noisy ingredients by careful screening. They can be stockpiled to smooth demand. They can be saved by rewriting the score. And they can be shared across modules by clean interfaces that move them without smudging. And just as with real tickets, counterfeits are worse than useless. They send the orchestra into dissonance, so authentication and timing matter as much as quantity. When you step back, a gentle lesson emerges. Universality in quantum computing is not a single switch you flip. It is a supply chain you build. Safe operations keep your memory coherent and your code space orderly, while magic states provide the sanctioned departures that make new logic possible. Ignore the supply chain and your program stall at the boundary of the simulable. Cultivate it, honestly, with good accounting and realistic thresholds. And your device gains the freedom to explore algorithms that cannot be flattened back into classical steps. In the end, the name magic is just an admission that we value what we cannot cheaply fake. And the craft is learning to produce, certify, distribute, and spend that value so skillfully that the extraordinary becomes routine, the rare becomes scheduled, and the spark that was missing lights the whole computation without burning it down. Resource theory of coherence. You start to feel what coherence really means when you imagine a choir singing not louder, but more in step. And the resource theory of coherence is the decision to treat that in-stepness as a tradable fuel with its own accounting rules. What counts as free to do, what costs you, what you can convert into what, always defined with respect to a chosen basis. The reference notes that your experiment or device naturally hears. Pick that basis, and the world separates into two kinds of states. Those that are already diagonal there, carrying only classical uncertainty about which note will sound, and those with genuine off-diagonal structure, where relative phases stitch alternatives together into a pattern that can guide interference, timing, and sensitivity. This difference is not philosophy, it is operational. If your lab can only perform incoherent actions, mixing, shuffling, measuring in the chosen basis, and forgetting the result, then you can never increase that in-stepness for free. Coherence becomes a currency that you must spend carefully, and the resource theory formalizes this with monotones, numbers that never go up under the free actions. So anyone claiming to create coherence from nothing can be checked by a simple audit that will not pass. Once you view coherence as currency, you begin to ask practical questions that have plain answers. How much coherence does a state hold relative to my basis? Think, how many distinct fringes could I, In principle, sharpen in an interferometer, how much coherence can I distill from many noisy copies into a smaller stock of nearly perfect on-demand pulses ready for metrology or computation? And conversely, what is the cost of creating a target state from scratch using only incoherent moves, plus a paid-for supply of coherence tokens? These paired quantities, distillable coherence and coherence cost, are the bookends of honest engineering, because they tell you whether your plan is even theoretically affordable before you draw a single circuit. The simple relatives used to measure coherence, one based on how far your state sits from the incoherent set, another based on how much structured surprise remains after you erase all off-diagonal terms, give consistent orderings and tight bounds in many cases, and they generalize to smooth versions for real experiments where small errors are acceptable, turning abstract definitions into lab-ready budgets. A striking insight arrives when you put coherence next to other resources. Under operations that are free for entanglement, coherence can sometimes be converted into entanglement between a system and an ancilla, and vice versa, but never with gain beyond the accounting rules. This bridge means that a single particle with phase coherence can be a seed for shared correlations if you have the right gates, while entanglement can act as a conveyor belt to move coherence where you need it. Similarly, coherence feeds metrology. A state with sharper relative phases can turn a faint rotation into a measurable shift faster, and the resource theory quantifies that gain, bounding the precision you can reach as a function of the coherence you inject and the noise you endure. In thermodynamics, coherence is not just heat dressed up. Time translation symmetry forbids you from turning pure phase structure directly into work without a clock-like reference. And the theory explains why some engines that look promising on paper in fact stall. Because without paying for a reference frame, you cannot align the phases across cycles, and the would-be fuel evaporates into dephased mixtures. Acquire a good reference and suddenly the door opens, with strict exchange rates that tie useful work to the coherence you consume and the entropy you create elsewhere. Because coherence is basis dependent, the same physical state can be rich or poor depending on what you plan to ask of it. And the theory leans into this honesty. You define your free set using the measurements and controls your device actually supports, not a pristine ideal and then compute budgets in that world. This prevents a common trap where you simulate heroic gates that your hardware cannot realize and declare coherence cheap, when for your lab it is not. In some platforms, noise has a bias. Phase noise dominates over flips, and coherence measures can be refined to respect that asymmetry, giving you thriftier protocols that protect precious directions and let cheaper ones suffer. You also meet catalysts, special states whose coherence enables transformations among other systems, but to an excellent approximation, returns unchanged at the end. These are not miracles, but carefully arranged assists that exploit structure without violating the monotones, and they can shave orders of magnitude off a factory's demand for fresh coherence if used sparingly and verified. The theory becomes even more intuitive when you tie it to tasks. In phase discrimination, coherence is the raw edge that makes two nearly identical rotations distinguishable. In clock synchronization, coherence sets how well two distant nodes can agree on tick marks without a direct comparison, and the free operations correspond to procedures that do not import hidden timing. In randomness generation, coherence that survives to the measurement stage produces outcomes that are provably unpredictable to an adversary who has no access to your chosen phase reference. And in quantum batteries, coherence inside the charger is the delicate asset that lets you move energy in a short, coordinated burst rather than through slow, classical trickle. Yet the same theory warns that if you charge in a way that sprays coherence into the environment, you will pay it back as heat somewhere else when you reset. Distillation of coherence looks familiar if you've seen other resource factories. Take many weakly coherent states, apply only the allowed moves, and post-select based on outcomes that signal when phases happen to align. The output is fewer, stronger pulses with fringe patterns that approach the ideal. Dilution goes the other way, spending a small number of crisp pulses to sprinkle gentle coherence across many targets for parallel, low-precision tasks. Limits on both processes are tight and often saturable with smart protocols, which means you can design to the resource bounds rather than guessing. And because some physical channels freeze coherence of particular states, leaving their in-stepness untouched, even as other features decay, you can place your information at those sweet spots and let the environment do less damage for free, a strategy supported by the theory's symmetry viewpoint. Speaking of symmetry, resource theory reframes coherence as asymmetry with respect to a group of transformations. If your free operations commute with a group, like time translations generated by a Hamiltonian, then states that change under that group carry asymmetry, which is just coherence seen through a wider lens. This unifies timing, phase estimation, and certain forms of sensing under the same umbrella, letting general theorems about asymmetry yield concrete consequences for coherence budgets. It also clarifies why you need a reference to exploit coherence. Without one, group averaging, dephasing, erases the very feature you hope to use, enforcing a kind of superselection that is not a ban on principle, but a statement about what your lab lacks. Bring the reference, pay for maintaining it, and the ban lifts along the exact lines the theory predicts. Day to day, the resource perspective changes how teams plan. Hardware groups report not only error rates, but dephasing spectra that tell software how fast coherence drains in relevant bases. Compiler teams arrange circuits to spend coherence right before it's read, not long before, and to store it in decoherence resilient modes when idle. Metrology teams design probe states by asking which coherence monotone best correlates with the Fisher information for their specific noise model, and then maximize that monotone under experimental constraints. Cryptography teams quantify how much coherence survives any side channel an eavesdropper might exploit, and how that translates into certified randomness or secrecy. And theorists supply conversion rates. How many rough probes by one sharp probe? How much timing coherence must be consumed to boost phase resolution by a given factor? How a biased bath changes the exchange prices? The style of thinking has a practical, calming side effect. It removes arguments about taste, this looks quantum to me, and replaces them with budgets that either balance or don't. If your proposed sensor claims doubled precision with the same resources, the monotones will demand to know where the extra coherence came from. If your algorithm seems to gain power after heavy dephasing, the allowed operations will reveal a hidden import of reference information you forgot to count. And if your architecture feels wasteful, the cost distillation gap will tell you exactly which stage leaks the most value and where a redesign saves the most. Hold finally the soft image that began this tour. Coherence is not volume, it is alignment. It does not shout, it sings together. Treat that togetherness as a resource and your designs become cleaner. Create it where it matters. Move it with care, spend it at the last moment, and account for it with measures that do not flatter you. And you'll find that clocks tick sharper, interferometers see dimmer shifts, protocols certify stronger promises, and the delicate order that quantum mechanics allows is used not as a metaphor, but as a disciplined fuel that you can refine, store, and deploy without illusions. Device-independent security from Bell tests. You don't really trust a lock until you can stop trusting the locksmith, and device-independent security is the quantum community's answer to that stubborn instinct. Build protocols whose guarantees do not rely on the inner workings of the hardware, but on patterns of measurement outcomes that even a malicious or broken device cannot fake without violating the basic no-signaling fabric of the world. And the way you test for those patterns is with Bell experiments. Imagine two sealed black boxes on opposite sides of a lab. No promises about what's inside, no calibration certificates you must take on faith, each with a knob that lets you choose a measurement and a light that flashes a result. And your only leverage is statistics collected when you and a partner choose inputs independently and quickly, far enough apart that no message traveling at or below light speed could coordinate the answers in time. If the correlations in the light's flashes cross a certain threshold that classical shared strategy gadgets can never surpass, you learn something remarkable without opening a single screw. Entanglement must be present, and more importantly for security, any eavesdropper, even one who built the boxes, cannot know the outcomes well enough to break your task without leaving a fingerprint in the numbers. The logic is at once simple and demanding. Classical boxes, no matter how cleverly pre-programmed, can only mimic a bounded level of correlation because their answers are limited to strategies that depend on local inputs and shared randomness. Entangled quantum boxes, by contrast, can cooperate in a way that outruns that bound. And if you see the violation cleanly enough, you can treat the outputs as fresh resources, secret bits for key, distribution or private randomness for lotteries, and simulations whose unpredictability is certified by the very impossibility of reproducing those correlations with local tricks. This flips the usual security story on its head. Instead of proving that a specific implementation is correct down to every component, you prove that certain impossible conspiracies did not occur, because if they had, the numbers would look different. Turning that idea into practice means treating every corner of the experiment as a source of potential loopholes, and then closing them decisively. You choose settings fast and unpredictably, so the devices cannot anticipate which knob you will turn. You place the boxes far enough apart and time the choices so that one side's knob twist and flash cannot influence the other before its outcome is sealed. You make detectors efficient enough that missing events do not allow a classical faker to hide behind lost data. You guard against memory and crosstalk, so yesterday's measurements cannot leak into today's choices. And you analyze all results with finite-sized statistics that recognize you did not run the test forever, assigning tight confidence intervals that account for randomness in small samples and for the possibility that a clever adversary could try to adapt over time. When these conditions are met, the raw violation turns into quantitative promises. A specific gap beyond the classical limit implies a specific amount of private randomness in the outputs and a specific bound on any adversary's knowledge about a potential key. Importantly, those promises are device independent, meaning they hold even if the internal dimension of the boxes is huge, even if the manufacturer mislabels components, and even if the devices were built by an adversary. As long as you trust space-like separation and the independence of your setting choices, the security reductions go through. This is why field trials of device-independent quantum key distribution and randomness expansion are celebrated milestones. They remove the most human part of the trust chain without removing the physics that makes secrecy possible. To appreciate the delicacy, consider what you do not assume. You do not assume the detectors are linear, or that the sources emit exactly one photon per pulse. You do not assume that noise is Gaussian. You do not assume that each trial is identical, and you do not assume no one tampered with calibration files. Instead, you assume that nature respects no signaling, that you shield information so settings are chosen privately, that you really achieved the timing needed for independence, and that you handled side channels like bright light control of detectors or radio frequency leaks that could smuggle inputs from one wing to the other. The discipline is harsh because the reward is strong. If the boxes pass, their outputs are usefully unpredictable, regardless of how the internals were implemented. From a systems view, a device-independent protocol is a pipeline. You run many Bell trials with randomly chosen settings. You compute a running statistic that tracks how far beyond the classical ceiling your data sits. You use this to lower bound the Min-Entropy of the outcomes, the adversary's best single-shot guess rate, and then you feed the outcomes through a public randomness extractor that distills uniform bits while provably bleeding away any residual correlation with an eavesdropper. In key distribution, you further reconcile mismatches between honest parties using error-correcting codes, and you sacrifice a slice of the data to estimate the violation with confidence. After which, privacy amplification shrinks whatever the adversary might still know to a negligible level. None of these steps requires opening the boxes, only careful bookkeeping and conservative statistics. In the wild, imperfections dictate design choices. Bright daylight and long fibers increase loss and threaten the detection loophole. So metropolitan tests use high-efficiency detectors and low-noise time bins. Long baselines increase the cost of space-like separation, but make setting choices safer, whereas chip-scale implementations trade space for speed, pushing nanosecond switching so signals cannot cheat. Some platforms prefer entangled photons for long distances. Others use trapped ions or solid-state defects for high-fidelity local operations. In every case, the architecture is judged by one number that matters for certification, the observed violation, and the rate at which it is accumulated with trustworthy independence, translated into secret bits per second or certified random bits per second, once finite size effects and extraction overheads are paid. Subtleties keep the field honest. Randomness begets randomness, so your setting choices must come from a source that an adversary cannot predict. Early steps can be bootstrapped with public randomness if you simultaneously run a spot-checking strategy that occasionally uses settings chosen by a weaker source, while reserving strong settings for certification. But the accounting must reflect any adversarial bias. Memory attacks, where boxes store previous inputs and outputs, are neutralized by analysis that allows arbitrary temporal dependence and still certifies entropy per round, as long as no signaling and input privacy hold each time, and free will loopholes where a cosmic or environmental signal might secretly influence. Both settings and devices are squeezed by choosing settings from independent physical processes and by timing them after any possible unwanted influence could have reached both wings, techniques that have even used starlight to push hypothetical conspiracies into absurd corners of the past. If your goal is practical key exchange for critical infrastructure, device-independent schemes are demanding today, but they point the way to security staples that need not ride on supply chain trust. If your goal is public randomness for science, lotteries, or cryptography, device-independent beacons can certify unpredictability in real time with audit trails anyone can check. And if your goal is simply to know whether your lab's entangler is truly entangling, a Bell-based self-test can certify the presence and quality of the resource with minimal modeling, a habit that reduces the surface area for mistakes. The deeper lesson is philosophical but actionable. By elevating independence, locality, and statistical rigor to first-class citizens, device-independent security turns the usual engineering question, "Do I trust this box?" into "Do I trust space-time and my own procedures?" Answer yes to those, and the rest follows with proofs, not hopes. Answer no, and at least you know exactly which assumption is too fragile for your application. Hold, as you leave, a quiet image of two distant lights flickering in coordinated defiance of classical limits. Every time their pattern crosses the bound, a sliver of certainty appears that no hidden script is guiding both at once, and from that sliver you can carve either secret keys or true randomness. You have not believed the devices because they looked honest. You have made them be honest by asking a question the world itself refuses to let a liar answer convincingly. Randomness expansion and amplification. You learn to respect chance the day you stop treating it as noise and start treating it as a resource you can mine, refine, and certify, and randomness expansion and amplification are the twin crafts that do exactly that. Beginning with a meager spark of unpredictability, a short seed you trust a little or a shaky source you half distrust, they produce many more bits whose surprises are provable, not just apparent. The first craft, expansion, asks whether a handful of honest coin flips can be stretched into a long stream that looks fresh even to someone who watched your entire setup, and the answer is yes. If you orchestrate two ingredients, a physical process whose outcomes can't be pre-written by shared scripts, and a mathematical press that squeezes out structure, an adversary might still hold. In modern labs, the physical core uses non-local games, the same style of trials that power Bell tests, to force devices to produce outcomes that no classical prearrangement can fake. You feed your small seed into the devices as a schedule of measurement choices, run many rounds where the two wings are kept independent in space and time, and check that the pattern of wins crosses the classical ceiling by a safe margin. Each round that contributes to that violation buys you a deposit of Min-Entropy, a lower bound on how unpredictable the raw bits are even to a malicious manufacturer who built the boxes with quantum-side memories. Then comes the press, a publicly known extractor. Think of a universal hash family like a large random Toeplitz matrix, or more sophisticated constructions that are provably safe against quantum holders of side information, which turns that lumpy, partially unpredictable stream into a shorter but almost uniform one. The miracle is not mystical. The physics certifies there must be entropy. The statistics tell you how much with finite sample uncertainty accounted for, and the extractor converts that quantified amount of surprise into clean random bits with a guarantee that holds even if an eavesdropper sat in the room and stored everything allowed by the laws of nature. Amplification pushes harder, starting from sources so weak that each next bit could be biased and even gently correlated with the past. The kind of imperfect coin that a cheap sensor or a human clicker might produce. Classical theory warns that from one such weak source, no amount of clever deterministic processing can conjure near-perfect randomness. But quantum non-locality reopens the door. By wiring several untrusted devices into a web of carefully chosen games and feeding them settings derived from the weak source, you can force outcome patterns whose very structure proves that the underlying bits couldn't have been too predictable. If the statistics clear specific thresholds, you upgrade a sketchy input into high-quality randomness. This is amplification. The cost is discipline. You must ensure the devices cannot whisper to each other during a round, that the setting choices remain hidden until the last moment, and that your analysis tolerates memory, drift, and adversarial adaptivity. Done cleanly, the pipeline produces private randomness from sources that would otherwise be unusable for cryptography or fair selection. Both crafts live or die by finite-size reasoning, not asymptotic dreams. You never flip coins forever. You collect a large but finite block of trials. You allow that nature jitters, and then you ask conservative questions. Given the observed violation and the number of rounds, what is the worst-case knowledge an all-seeing adversary could still hold? And you answer with the entropy accumulation framework and related tools that add up per-round guarantees while tolerating dependence between rounds. That bound becomes your budget for extraction. Choose parameters too aggressively, and you risk output that only looks random to you. Choose them honestly, and you know exactly how many secret bits per second you can promise at a given confidence. Engineering details matter, and they steer designs in recognizable ways. Fast and efficient detectors raise detection rates and close loopholes that would otherwise let classical cheats hide inside missing events. Space-like separation or nanosecond fast switching of settings prevents messages from coordinating answers. Balanced timing and shielding defeat, radio frequency and optical side channels. Calibration routines keep drifts from silently eating your violation margin. And spot-checking schedules, where most rounds are used for certified generation, while a randomly picked fraction are used to test the game score, let you build long outputs without pausing for constant audits. When losses climb on city fibers, you shift to time-bin encodings and superconducting photon counters. When you run on chips, you trade distance for speed, pushing sub-microsecond cycles to keep the independence assumptions safe. In every architecture, the scoreboard that matters is simple. How far above the classical line your data sits after accounting for all finite sample penalties, translated into extractable secret bits after the press. The small seed needed to launch expansion has its own logic. You must pick settings in a way the devices couldn't anticipate. That does not mean you need a perfect seed. Short, slightly biased seeds can be lifted by carefully designed protocols that borrow a tiny amount of trust and repay it with a huge dividend of certified bits. But you must account for any bias in the analysis. Clever schemes recycle part of the newly minted randomness to fuel the next block's choices, achieving in principle unbounded expansion from a constant size seed under stable conditions. Here again, the extractor is your friend twice over. It not only purifies raw outcomes, but can also refresh the seed itself, so the next round's choices are as surprising to the devices as the first. The flow begins to look like an assembly line. Seed in, choices out, trials run, violation checked, extractor pressed, random bits banked, a slice fed back as the next seed. And every stage has dashboards with error bars rather than hope, because these bits are intended for serious jobs: cryptographic keys, public beacons, secure lotteries, scientific sampling. Composability matters. The guarantees must survive when the output is fed into larger protocols and when an adversary times their actions based on public announcements. Modern statements, therefore, package the result as a bound on the adversary's optimal guess probability, conditioned on everything they might know. A promise that holds whether the bits guard a one-time pad or seed a Monte Carlo engine. The public extractor seed and the observed statistics can be published without risk, because their only effect is already accounted for in the bound. What remains secret is the final extractor output, which, by design, looks new even to someone who built the boxes. Alongside these core paths, you'll find variations that put the same idea to work in different climates. Randomness beacons that continuously publish certified bits with signed audit trails, so anyone can check the violation curves before trusting the stream. Satellite-assisted schemes that stretch baselines to the sky to make independence trivial while using ground stations to close detection losses. Networked protocols where several labs contribute to a joint public randomness pool, such that no single compromised node can bias the outcome without being exposed by the combined statistics. And device testing routines that, while not full generators, quickly flag when a source's unpredictability is dipped below a safe line. A practical guardrail for facilities that rely on randomization day and night. There is also a quiet, important connection to weak randomness models from computer science. When a source promises only that no single future bit is overly predictable, even given the past, an assumption still far from ideal, quantum amplification can nonetheless convert it into nearly unbiased output, something provably impossible by classical post-processing alone. The quantum edge here is not hand-waving mystery, but the enforcement of constraints by no signaling. Because spatially separated events cannot coordinate fast enough, any classical forgery leaves a distinct fingerprint in the game score that statistics will catch if you watch long enough. In this way, physics becomes a referee for information promises, elevating cautious, worst-case definitions into workable pipelines. By now, the pattern should feel solid. You begin with a small or suspect spark. You challenge untrusted devices with questions they cannot all answer too well without breaking the rules of the world. You translate the observed honesty into a quantitative uncertainty budget, and you refine that budget into clean bits using an extractor that bleeds out any structure an adversary might still hold. No step asks you to believe internal schematics, only to believe procedure, timing, and space-time itself. And the product is not random looking, but random by proof, resilient to hindsight and audit. Hold one last image as the room quiets. 2 distant stations, clocks ticking, choices made at the last possible moment, detectors blinking in patterns that edge past what any shared script could achieve. From those blinks you don't take comfort. You take certified surprise, stretch it from a trickle to a river, and leave with a stream of bits that can anchor secrets, steer fair decisions, and seed science without leaning on faith in boxes or brands. That is randomness expansion and amplification. Not a slogan, but a discipline for turning fragile unpredictability into a dependable commodity. Quantum one-time pad and secret sharing. You learn what it means to hide something perfectly when you imagine, placing a message into a ripple of water and then stirring. Just enough that no one, no matter how clever, can tell what the ripple once was. And in quantum information, that precise kind of hiding is the quantum one-time pad. A simple, physical recipe that turns any qubit, or even an entangled share of a larger system, into featureless noise for anyone who lacks a tiny classical key. The idea is operational rather than mystical. For each qubit, you flip a fair pair of classical coins to choose one of 4 scramblers that, together, randomize both the visible digit and the hidden phase, so completely that the ciphertext is indistinguishable from thermal background. And crucially, you need 2 key bits per qubit, because quantum states carry 2 independent directions of structure that an eavesdropper could test. Classical pad for digits alone would leave telltale fringes. The guarantee is information theoretic. Without the key, no measurement, no adaptive strategy, no side calculation with quantum memory can reveal anything about the plain text beyond its length. And this remains true even if the message was part of a larger entangled state. Scrambling your share erases all accessible correlations to outsiders while leaving the joint state recoverable for the key holder. With the key in hand, decryption is as gentle as running the chosen scramblers in reverse, restoring the exact state so that subsequent interference and computation proceed as if the world had not looked. But security has two faces: secrecy and integrity. And here honesty matters. A one-time pad, classical or quantum, hides content but does not by itself flag tampering. So practical designs pair the quantum pad with lightweight authentication, appending stabilizer-style checklines or trap qubits that alert you if a meddler nudged the ciphertext on its trip. If the check passes, you can even recycle much of the key, because the successful verification proves no information leaked. A thrifty habit that matters when keys are precious and devices are slow. The one-time pad becomes more than a textbook footnote when you build systems around it. Long-distance links apply the pad before sending fragile states through lossy fibers. Storage nodes encrypt data at rest so that a stolen memory chip reveals only white noise, and cloud workflows wrap intermediate states so that idle qubits on someone else's hardware carry no clues about the computation. Because the pad operates locally on each carrier, it scales across architectures: photons in time bins, spins in solids, superconducting circuits, so long as the scramblers can be implemented cleanly, and the tiny key can be kept truly secret and truly fresh, and key management is not hand-waving. Keys can be provisioned by pre-shared material, by information theoretic key exchange run beforehand, or by physically carried vaults. In every case, composable security proofs let you treat the pad as a black box that leaks nothing, even when the rest of your protocol is public. The same style of guarantee you demand from a good classical cipher, but now grounded in the physics of indistinguishability. If perfect hiding is one pillar, secret sharing is the other. Instead of trusting a single custodian, you scatter a quantum secret across several holders so that only authorized coalitions can reconstruct it, and every smaller group learns nothing at all. Unlike classical schemes where bits can be copied and split freely, quantum secret sharing must respect no cloning and therefore uses encoding rather than duplication. The dealer embeds the secret into an entangled state whose structure mirrors a chosen access policy, hands out physical shares, and guarantees that reconstruction requires the right quorum and the right joint operation. In threshold form, you might say any 3 of 5 can recover, any 2 or fewer are blind, and you realize this by borrowing blueprints from quantum error correcting codes. The same geometry that lets a code tolerate up to 2 errors also lets it withhold all information from any 2 participants, while ensuring that 3 can run a public decoding circuit to retrieve the state. More broadly, stabilizer and graph state constructions implement rich access structures, not just thresholds, by deciding which measurements on which subsets unlock the correlations that define the secret. For unauthorized sets, the math and the lab agree. Every measurement statistic they can collect is exactly what they'd see if the dealer had sent them random junk, a strong, audit-friendly meaning of no information. Real schemes are pipelines rather than magic tricks. The dealer first prepares verification traps mixed into the encoding to detect a dishonest player or a mischievous channel. Each participant performs only local, simple operations and reports classical readouts. Reconstruction is a fixed recipe that never requires a peek at the secret halfway. And because life is noisy, the encoding doubles as protection. If a few shares suffer loss or mild decoherence, the authorized set can still succeed, while unauthorized sets remain locked out by design. If your application is governance of a key, you might share a quantum secret that acts later as a gate to unlock a receiver's decryption tool only when a committee agrees. If your application is custody of a sensor state, you might distribute it so that only a full team can bring it back, preventing any one lab from running a measurement alone. If your application is archival, you might spread a state across distant vaults and schedule periodic refreshes where the holders jointly error correct and re-encrypt to roll forward against slow drift, each step leaving no usable residue outside authorized coalitions. The 2 pillars meet naturally. You can one-time pad each share before distribution to ensure that even a compromised courier learns nothing on the way. You can authenticate each leg so tampering is caught at the edge rather than discovered at reconstruction. And you can prove composably that the combined system still reveals nothing to an adversary who intercepts some, but not enough shares, and later obtains all public logs. You also gain policy control that classical tools can't mimic cleanly. Because reconstruction requires joint quantum action, you can enforce that quorums meet physically or via entanglement-assisted links, and you can rotate the access structure over time by moving holes in the underlying code's layout, adding or removing authorized paths, without ever decrypting the secret in the clear. And when participants retire or devices are replaced, you run a privacy-preserving resharing that changes who holds which pieces, while provably keeping the secret hidden from any old or new minority. Honest limitations steer design. A one-time pad is only as good as its key hygiene, reusing. The same 2 bits for the same qubit, twice-leak structure, just as in the classical world. So key. Derivation and auditing must be treated as first-class citizens. Authentication adds overhead, and in practice you choose check densities that match your channel's tamper risk. Reconstruction circuits require coordination and reliable timing. So distributed teams build playbooks for failures that pause decoding before a partial view leaks. Procedures that are as much human as technical, and access structures obey physics. No scheme can allow 2 disjoints. Majorities to each reconstruct the same unknown state at the same time without breaking fundamental limits, so threshold parameters are chosen with those constraints in mind. If you want a concrete mental model that balances the math with the human needs, picture a museum storing a fragile hologram. The quantum one-time pad is the opaque wrap that makes any stolen packet look like empty film. Quantum authentication is the tamper-evident seal that tears if someone tries to peek. And secret sharing is the policy that says the hologram can only be unwrapped when the right number of curators, each holding a different corner, lift together under the skylight, make the wrap fresh each time, check the seals at every handoff, require a quorum to open, and you have a workable, provable path from first principles to practice. Hiding content absolutely, detecting meddling promptly, and distributing trust so that no single failure can bring the whole picture into view. Carry that image, and the terms quantum one-time pad and secret sharing stop sounding like arcana and start reading like straightforward tools for a world where information is not a thing you copy and pass around, but a delicate pattern you either protect jointly or lose forever. Blind quantum computing, outsourcing safely. You learn what real privacy feels like the first time you imagine sending a problem to a powerful quantum lab you do not trust and still sleeping well. And that is the promise of blind quantum computing. You, the modest client, prepare or shape tiny hints of quantum states and short classical messages so that the server does the heavy lifting, while learning essentially nothing about your input, your algorithm, or your output. The cleanest way to picture it is measurement-based computing turned inside out. You supply the server with a sea of simple qubits whose orientations are secretly randomized by you. The server stitches them into a large entangled canvas and performs measurements you request. And because your requests are masked by fresh randomness, every instruction the server sees could equally well have come from many different computations. Blindness here is not a slogan, but a precise guarantee. Conditioned on everything the server touches, the distribution of what they observe is compatible with a huge set of possible tasks. So their best strategy is to compute correctly if they want to be paid. The practical recipe behind the first universal schemes is disarmingly concrete. Prepare single qubits with angles you choose at random, send them to the server, ask the server to connect them into a brickwork-like pattern, and then stream measurement angles that are also hidden behind random shifts. Your hidden angles cancel the random masks you injected earlier only in your own accounting, so the true computation unfolds for you while the server sees a blur. Because randomization is per qubit and per round, even a malicious server that records everything cannot piece the secret back together later. And if you worry about correctness as well as privacy, you lace the canvas with trap qubits placed at locations only you know. When the server reports the outcome on a trap, you can check whether it aligns with your private expectation. and a single inconsistency can condemn an attempted cheat with high confidence. This gives you verifiable blindness, the twin goals of secrecy and detectable misbehavior, without demanding that you ever reveal your algorithm or intermediate states. Not every client wants to prepare qubits, so variants shift the burden. In measurement-only designs, the server generates and streams qubits to you, and you merely measure them with private angles, which still blinds the task because your local choices are never shared. In double server versions, you keep a purely classical role while two non-communicating quantum servers, who may even be controlled by the same adversary, perform a choreographed dance that is blind to both of them individually. And in a different vein altogether, there are protocols where a classical client gains verification power by asking a single quantum server to produce answers whose correctness can be certified through carefully designed challenges that no classical faker can satisfy. A milestone that turns trust the cloud into challenge the cloud. Across these designs runs the same quiet theme. Security is rooted in physics and randomness, not in brand labels or insider access. And every message you send is deliberately noisy to everyone but you. Turning this into a usable service means solving engineering puzzles that feel familiar once you name them. Synchronization, so that your randomization cancels at the right moment. Device calibration, so preparation or measurement errors don't leak tiny patterns that a patient server could exploit. Authenticated classical channels, so the server cannot spoof your timing or swap instructions. And fault tolerance woven into the protocol, so that your traps and masks survive the noise of real hardware. Advanced blueprints even combine blind computation with quantum authentication, wrapping your delegated data in signatures that detect tampering before it reaches sensitive parts of the circuit, and with error-correcting encodings, so that you can space out traps among syndrome measurements and catch mischief without derailing the computation. The overhead is honest. You will send more qubits and more classical messages than the bare algorithm would suggest, and you must keep high-quality randomness on hand. But the trade is clarity. You scale trust down to a crisp set of assumptions, e.g., you can make or measure simple qubits. The servers cannot talk behind your back, your random seed stays private, and you get proofs in return. Blindness is not only about hiding inputs, it also hides structure that a vendor might otherwise deduce. Your model architecture, your chemistry ansatz, your objective function, so companies can outsource proprietary workloads without handing over their playbooks, and researchers can run sensitive analyses without revealing which hypotheses they are testing. In federated or multi-tenant settings, blindness dampens side channels. Even if a provider monitors resource usage or gate counts, the masks smear those signatures, making it harder to fingerprint clients by the shape of a job. In government or medical contexts, blindness supports audit trails that show a computation was run and verified without exposing the data itself, a form of compliance that leans on mathematics rather than non-disclosure agreements. There are limits, and they are instructive. Perfect blindness with a purely classical client and a single untrusted server is too much to ask from physics alone if you also want universal, non-interactive computation. So practical designs either give the client a tiny quantum capability, add interaction and traps, or assume two separated servers. Fully homomorphic encryption for quantum circuits, the dream of uploading an encrypted quantum program and getting an encrypted result back in one shot, remains an active research area with partial progress, but not yet a general efficient tool. And modest leaks can creep in if your random number generator is weak, if your qubit source drifts in a way correlated with your secret angles, or if the server can infer timing patterns from your classical messages. The antidote is procedural. Certify or refresh randomness with extractors, pad and schedule messages to flatten timing, and periodically self-test your own devices by tasks whose results you know in advance. When you adopt those habits, the remaining assumptions are explicit and defendable. The road to scale blends theory and architecture. Compilers restructure target circuits into blind-friendly forms that minimize costly round trips. Resource estimators account for the extra qubits and classical bandwidth associated with traps and masks. Schedulers arrange batches so that factories for special resource states feed the delegated core just in time without revealing when the interesting moments occur. and network designers co-locate repeater nodes and timing references so that spatial separation for multi-server protocols is easy to maintain. In parallel, verification theory keeps tightening finite-size bounds so clients can stop a run early with confidence when enough evidence has accumulated, rather than paying a full fixed cost every time. In daily practice, a blind workflow reads like a ceremony. You initialize your private randomness. You either prepare or measure simple qubits with angles only, You request the server to entangle and measure according to your masked instructions. You sprinkle tests whose expected outcomes only you can predict. And you decode the final classical report into the answer that the server never saw. At no point do you peek at intermediate quantum data that would collapse what you are trying to compute. And at no point can the server rearrange the steps to glean structure without tripping a trap. What you rely on is not their goodwill, but the fact that any deviation that could teach them something specific about your secret would also lift a statistical flag in the places you designed for exactly that purpose. Perhaps the softest way to carry the idea is this. Blind quantum computing is not about hiding in darkness. It is about lighting only the rooms you need when you need them. You let the untrusted building supply power and space, but you carry your own keys, your own dimmers, and your own checklist at the door. Done well, the server sees motion but not meaning, activity but not aim, work but not the reason for it. And when the result arrives, decoded by you, verified by traps you planted, and certified by bounds that tolerate real-world noise, you end with the calm that started this journey. You got the benefit of someone else's machine without adopting their risks, and you did it by designing the flow of information so carefully that curiosity had nowhere to stand. Position-based cryptography. Can location be a key? You've used a password, a fingerprint, maybe even your face. But what if the only credential you needed was being in the right place at the right time and nothing else? That is the provocation behind position-based cryptography. An ambitious idea that treats location itself as a key by challenging a prover to respond to timed questions so quickly, and from such geometry that only someone physically sitting in the claimed spot could possibly answer in time. The backbone of this hope is simple physics. Signals cannot outrun light. Hardware cannot anticipate questions it hasn't received. And if several verifiers scatter around a map and shoot synchronized challenges, the round-trip delays stitch a triangular truth that a distant imposter cannot fake. In its most down-to-earth form, this shows up as distance-bounding protocols used to repel relay attacks. Think of keyless car entry or contactless payments where thieves try to act as cables, forwarding your device's messages from far away. And the fix is to ask the device to answer micro-challenges with nanosecond precision, so any extra hop adds a telltale delay. Real systems use ultra-wideband pulses, carefully randomized bits, and tight clocks to catch early detect, late commit tricks, where an attacker guesses or partially forwards. And designers worry about every analog corner. Multipath reflections that can mask extra time, jitter that smears edges, radio power that lets a distant station eavesdrop, and synchronization errors that leak timing secrets. The scientific heart, though, lives one level up. Can multiple verifiers, placed at known coordinates, extract enough timing structure from a prover's replies so that no coalition of off-site adversaries can impersonate someone at the target position? Classically, the answer is brutal. If attackers can coordinate and share messages arbitrarily fast before the protocol starts, then during the challenge, they can split work and stitch together correct answers on time. So pure location as a key collapses under collusion. That impossibility pushed researchers toward quantum tricks, because quantum information obeys constraints that classical data does not. You cannot in general clone unknown quantum states, and measuring them in the wrong way destroys the patterns needed to answer later questions. Quantum position verification, QPV, builds on this by having verifiers send carefully chosen quantum states from different directions so that only a party at the claimed location, who receives all pieces in the right time window, can perform the correct joint operation and reply before the deadline, while attackers stationed apart cannot both hold the states and combine them fast enough without either copying, forbidden, or measuring early, which ruins them. The The plot twist is that quantum mechanics gives and takes. While no cloning blocks naive copying, a coalition of adversaries that shares enough entanglement beforehand can teleport quantum pieces around almost instantly once the classical messages arrive, effectively knitting a virtual lab at the claimed location. Elegant no-go theorems show that with unlimited pre-shared entanglement and perfect coordination, attackers can defeat any position-only scheme in principle, meaning unconditional, assumption-free location as a key is impossible. Yet impossibility theorems are guide rails, not dead ends. If you bound the adversaries, limit their entanglement stock, cap their local dimension, constrain their memory coherence time, or make them pay communication latency between sites, then QPV protocols regain teeth. The security promise shifts from absolute to resource-bounded. To fake your location, attackers would need an unrealistic warehouse of high-quality entanglement, noise-free memories, and sub-nanosecond orchestration, which you can push beyond what's practical by tuning the protocol's rate, dimension, and error tolerance. Hybrid designs even combine relativity, space-like separation of verifiers, with quantum state so that any classical coordination between attackers is too slow and any quantum attempt burns through entanglement faster than they can maintain. On the engineering front, making location a usable credential means building a pipeline rather than a stunt. Verifiers must share precise clocks or run clock sync sub-protocols with audit trails. Challenge bits must be generated from entropy sources no attacker can predict, and the prover's hardware must be simple enough to keep trust assumptions small. A tiny phase shifter and detector rather than a full computer. Protocols randomize challenge bases so that predict and pre-compute strategies fail. Inject decoy rounds that expose wormholes, covert relay boxes, and adaptively tighten thresholds if the radio environment gets noisy. In urban canyons, where reflections stretch path lengths, systems lean on antenna diversity and time of arrival statistics to distinguish direct paths from echoes. Where fiber is available, verifiers distribute timing signals over stabilized links to shrink drift. And wherever RF leaks could betray settings, shielding and protocol padding flatten the side channel landscape, so attackers glean no preview from power or timing patterns. All of this is paired with conservative finite sample statistics. You don't run forever. You run a lot, you bound false accept risk under worst case noise, and you only mint a location credential when the numbers clear a bar you set beforehand. The quantum layer adds its own practical knobs. You tune photon rates so losses don't hand. Attackers cover under the detector efficiency. Loophole. You interleave classical sanity checks that force would-be cheaters to reveal themselves if they try to use bright light tricks on detectors. And you position verifiers so that honest prover light cones overlap correctly, while any coalition separated by more than a few hundred meters faces causality walls that squeeze their options. Where entanglement sharing between attackers is plausible, say short-range labs, you drive up the temporal bandwidth of the protocol so that maintaining enough high-fidelity entanglement long enough becomes the bottleneck. Where long distances are involved, satellite links help. Verifiers on ground stations with a satellite relay can create geometries that adversaries cannot replicate without astronomical resources. And in deployments that mix classical distance bounding with quantum tests, you can gate access in stages, fast RF timing to swat away simple relays, then occasional quantum state challenges as audits that a well-resourced thief cannot comfortably pass. Just as important as the physics are the threat models you declare up front. Are you defending against a single relay team or a fleet with lab-grade gear? Do you assume attackers can place devices arbitrarily close to verifiers, or do you secure perimeters? Can they pre-share a bounded number of entangled pairs, or do you budget for more? Clear answers turn philosophy into architecture. Likewise, you decide what privacy means. Some applications want location proofs without revealing the location itself, so protocols release only yes-no in-region certificates derived from geometry, often using zero-knowledge wrappers. Others want linkability controls so that a commuter's car cannot be tracked across checkpoints by the signature of its timing hardware. Still others want transparency for audit. Verifiers publish anonymized timing logs, so third parties can verify no funny business occurred. These policy layers ride on the same core. the physics of timing, and the structure of quantum states. But they decide whether the system serves people or merely surveils them. You should also carry forward the honest limits. GPS-style multilateration can be spoofed if verifiers are not securely authenticated. RF distance bounding can be bent by analog front-end tricks unless you shake challenges too quickly for prediction. Quantum schemes cannot beat the fundamental no-go theorems without assumptions, so every security claim must boldly list which resources are bounded and how those bounds are enforced in reality. And every field deployment must tolerate lossy, jittery channels without lowering thresholds so far that relays slip through. The art is in the margins, raising your violation of relay plausibility above what any reasonable attacker can hide while keeping honest users inside the acceptance window. In the end, asking, "Can location be a key?" turns out to be a way of asking a deeper question. How much of trust can we anchor in the fabric of space and time? And how much must we still place in devices and people? Classically, location alone cannot bear the full weight if adversaries collude without constraint. With relativity and quantum rules in play, location can carry a surprising share, enough to build locks that reject the most common cheats and even deter sophisticated teams, unless they bring resources few possess. The gentle takeaway is practical rather than mystical. Treat distance of flight and space-like separation as enforcers. Treat quantum tests as friction that makes collusion expensive. Publish your assumptions, measure like an accountant, and you can use place not as a password you whisper, but as a physics-backed promise that someone is truly there, right now, exactly where your policy says they must be. Quantum money, unforgeable by physics. You don't need a watermark or a hologram if the paper itself refuses to be copied, and that is the arresting promise of quantum money. Banknotes, whose ink is a pattern of quantum states that physics will not let a counterfeiter duplicate or even probe without damage. So value is protected not by secrecy alone, but by the structure of reality. The seed of the idea dates to an era of slide rules, when Stephen Wiesner imagined each note carrying a classical serial number plus a handful of microscopic systems, say photons or spins, prepared in bases known only to the mint, and a verification test that checks them in exactly those secret bases. A genuine note sails through because it was minted with the right orientations, while a thief who tries to read and reprint stumbles. To learn the hidden basis you must measure, and measuring in a guess basis gives you only partial truth and leaves irreversible scars. Try to copy before learning, and the usual printing press logic fails because unknown quantum states cannot be cloned on demand. The result is not superstition, but an operational trap. The more a forger touches, the less they know for sure, and the worse their replicas fare at the bank's check. Information and disturbance are coupled, so look without leaving fingerprints is no longer an option, and the bank can detect the tampering statistically with only local tests tied to the serial number's secret recipe. Bringing this sketch to life mixes physics with accounting. You want notes that survive handling and time, so verification must tolerate small lab errors without letting cheats slip through. You want the bank's database of secret bases to be manageable and revocable, so lost notes don't force mass resets, and you want minting to be fast enough that value can be issued at scale. On photonic platforms, for example, a note might store a sequence of single photon polarizations or time-bin superpositions embedded in a tamper-evident card, with the mint's log recording which basis each position used. A merchant authenticates by sending the quantum portion through a reader whose settings are keyed by the serial, receiving a sequence of clicks that match an expected pattern more often than any fake could produce. Because real devices lose photons and drift, the test accepts a band of outcomes and accumulates evidence across many positions rather than trusting a single shot. Because repeated checking also risks wear, advanced designs include gentle verifiers that randomize which subset they test, or that perform non-demolition checks where hardware allows. Still, there is always a trade. More tests means stronger confidence, but more exposure of the fragile states. So policies cap the number of verifications per note or require periodic refresh at a mint terminal that re-encodes the quantum data under a new serial while certifying the old one as spent. The dream grows bolder with public key quantum money, Banknotes anyone can verify with public instructions, yet no one but the mint can forge. Here the secret basis trick is replaced by deeper structure. States chosen from hidden subspaces, not like invariants, or families pegged to cryptographic oracles, so that a public test recognizes the right pattern, but does not reveal how to manufacture fresh instances. In theory models where the verifier can query a special function, researchers have proposed and analyzed such schemes, proving that forging would require solving a problem believed intractable even with quantum tools. In the fully standard setting, the story is harder. Candidate constructions exist under assumptions about hash functions, lattices, or so-called quantum lightning. But turning them into practical, tamper-proof notes with tight, real-world proofs remains an open frontier. Still, progress has already paid side dividends. Techniques for self-testing unknown states, certifying high-dimensional structure, and amplifying small verification gaps. All ingredients you also see in secure randomness beacons and delegated computation were sharpened by attempts to mint public money. Honest obstacles shape the engineering. Storage is brittle since most quantum states decohere. So many prototypes lean on online money that is minted on demand and verified immediately for transfer, closer to bearer tokens than to cash in a drawer, or on photonic tokens stored as classical recipes at the bank that produce fresh states for each authentication. Loss is a fact, so protocols budget for missing detections without opening a path for a counterfeit to pass by claiming bad luck. Reuse is a risk, so schemes limit how many times the same quantum carrier may be shown, mixing classical audits with physics to prevent slow degradation from becoming a forgery route. And side channels matter. A clever adversary might try to glean basis information from tiny correlations in timing, temperature, or light leakage, so readers randomize order, equalize power, and blind detector tricks are blocked with watchdog pulses and sanity checks. Crucially, double spending is policed in the classical layer. Serial numbers are marked in flight during a transaction and retired when a note is refreshed, while the quantum layer enforces unforgeability. Even if a thief steals a snapshot of a genuine note, they cannot mint two that pass verification at once, because any attempt to inspect and replicate will spoil whichever copy is examined next. The policy surface is as important as the physics. Central banks would need procedures for revocation, e.g., if a batch's secrets leak, for reissuance after accidental damage, audit the prior checks, then swap for a fresh note. And for privacy, readers should prove validity without logging the exact measurement outcomes that could fingerprint a note across shops. Auditors need assurances that the Mint's database can't be abused to track individuals. So zero-knowledge wrappers around verification logs can show that a valid check occurred without revealing which positions were tested. Merchants need service-level numbers that acknowledge finite statistics. With this many tested qubits and this observed match rate, the chance of a clever fake passing is below 1 in a billion, figures that can be standardized and inspected. And users deserve clarity that a quantum banknote is not magic that never fails, but a system with crisp error bars where each step, issuance, storage, verification, refresh, has a controlled, transparent risk that composes. Even if full public quantum cash remains elusive, the token viewpoint is already useful. A bank or platform can issue quantum tickets that unlock actions, enter a secure area, run a computation, retrieve a credential, exactly once. Because a ticket cannot be copied, fishing for duplicates is fruitless, and because verification can be local, no network needed. Offline settings benefit. Tie a token to a time window or replace via distance tests, and you get layered protection, resilient to both duplication and relay. And mix quantum authentication with classical one-time pads around the control messages, and an attacker who tampers with transit is revealed immediately rather than at settlement. The philosophical punchline is quiet but strong. Classical anti-counterfeiting is a race of patterns against pattern recognition. Quantum money changes the game by using patterns that cannot be read and reprinted without leaving a trace. Scarcity comes not from obscurity, nor from secret ink that scanners haven't learned yet, but from the impossibility of copying certain kinds of physical information on demand. In a world awash with perfect classical copies that shift matters, value anchored in laws, not logos, and trust derived from procedures anyone can test. Picture, as you finish, a modest card sliding into a reader, the device asking a few carefully randomized questions, a hush of single clicks answering back, and a small green light that means not, "We recognize this pattern," but "We just asked the universe whether this could be a counterfeit, and the universe said no." And let that calm answer be the point where physics, policy, and practicality meet to make money that's unforgeable for reasons deeper than ink. Tomographic security and side-channel pitfalls. You only understand how exposed a quantum system can be when you try to prove it is what it claims, and realize your proof is only as strong as the questions you asked. And that is the heart of tomographic security and its side-channel pitfalls. Tomography, whether of states, processes, or whole gate sets, is the family of laboratory X-rays we use to reconstruct what a device does by shining many well-chosen probes and reading many outcomes. And it is powerful, but its guarantees live inside a model, while attackers, noise, and even innocent design quirks often live outside it. In state or process tomography, you assume you can prepare known probes, apply the device, and measure in bases that together reveal the object of interest. Then use statistics to rebuild the unknown with error bars. In gate-set tomography, you drop the fiction that your probes and meters are perfect, and instead learn them along with the device under test, producing a self-consistent portrait that resists common calibration traps. In compressed sensing variants, you exploit sparsity or low effective rank to cut the number of settings dramatically. And in shadow methods, you trade detail for speed by estimating only the observables you care about. All of these are indispensable for commissioning hardware, catching drift, and certifying performance before you entrust a platform with valuable states or keys. Yet every one of them rests on quiet assumptions. That errors are roughly stationary during the run, that trials do not remember each other, that the device has no context dependence on hidden knobs like temperature or recent history, that the channels you probe are the only ones that matter. When those assumptions strain, tomography can paint an image that is internally consistent and still dangerously incomplete. Side channels are where reality slips through the seams. A photon source that occasionally spits light at wavelengths your filters ignore. A detector whose timing jitter reveals which basis you chose. A control line whose power draw whispers whether an ancilla flipped. A qubit chip that hums imperceptibly louder when a particular state is loaded. A back reflection that carries a faint copy of your setting choice down the fiber to the street. None of these show up in the tidy model unless you looked for them. And an adversary does not need to defeat your cryptography if they can listen to your hardware's gossip. Even without malice, leakage can sabotage protocols by correlating rounds that analysis assumed were independent, or by skewing outcome frequencies in a way that perfects your calibration but falsifies your security proof. In optical platforms, classic pitfalls include Trojan horse light sneaking into modules and returning imprinted with your choice of phase, bright light tricks that push avalanche detectors out of their intended regime, and wavelength-dependent loss that turns a fair coin into a biased one. In solid-state devices, microwave lines leak tiny amounts of information to room-temperature electronics. Control pulses nudge neighbors through crosstalk, and thermal management leaves slow fingerprints that a patient observer could correlate with your secret schedule. Even software layers betray you. Operating systems, time slice, caches warm up, clocks drift. And if your security rests on random choices generated by a weak or misconfigured source, tomography on the quantum core will not save you from a classical guesser who can predict those choices. The cure is not to abandon tomography, but to harden its contract. Broaden the model, diversify the probes, and pair reconstruction with independent monitors that watch for torque you did not authorize. Practically, that means mixing tomographic settings with sanity probes that never enter the reconstruction, but are designed to light up when side channels misbehave. Like sending occasional dark frames to detectors and confirming they stay quiet, inserting calibrated bright pulses to ensure watchdogs catch attempted blinding, sweeping rare wavelengths to check filters, and measuring power, RF, and acoustic signatures while toggling settings to confirm no telltale modulation escapes. It means randomizing the order and timing of tomographic configurations, so slow drifts cannot be mistaken for device features. Padding message schedules so that a remote observer cannot infer which basis you chose from packet cadence, and equalizing pulse shapes and powers across settings so that energy use carries no labels. It means placing optical isolators and attenuators at ports that should be output only, and adding tap detectors that raise alarms if unexpected light tries to enter. It means using differential measurements to cancel common mode leaks in multi-qubit chips, and adopting shielding and ground discipline so that neighbors cannot eavesdrop through shared impedance. And it means auditing your randomness with extractors that convert messy entropy into near-uniform choices and reporting the audit alongside the tomography, so downstream, users can judge whether your settings truly were unpredictable. On the estimation side, you treat finite data honestly. You report confidence intervals that reflect not just shot noise, but model mismatch. You repeat the full reconstruction on interleaved days to sniff out non-stationarity, and you perform out-of-sample tests by predicting statistics for settings you did not use during fitting and then checking them. Gate-set tomography helps here because it reveals when your supposed known preparations and measurements drift, and contextual tomography, where you label data by environmental tags like temperature band, time since last reset, or which neighboring controls were active, shows whether what you thought was one device is actually a family of slightly different ones. When memory effects are strong, you abandon the comfort of independent trial models and adopt protocols designed to expose history dependence, such as randomized compiling that scrambles coherent error into benign noise, or specialized sequences that probe echo-like behavior. And when a protocol's security hangs on specific symmetries, for example, that two measurement choices are truly indistinguishable to any outsider, you prove those symmetries with independent equipment, different detectors, different power meters, different labs, because single stack confirmation is too easy to fool unintentionally. Tomography can also be turned into a guard, rather than a mere microscope. Before a critical run, you reconstruct a fingerprint of your source or gate, and then monitor a small set of witness observables in real time, each chosen for high sensitivity to known failure modes. If any witness drifts beyond a tight band, you pause the protocol, investigate, and only resume after a fresh calibration. In networks, you distribute witness checks across nodes, so a local compromise cannot fake the health of the whole. And in outsourced settings, where a vendor performs the experiment, you require raw logs and perform your own reconstruction, asking for challenge rounds with settings you pick at the last second. Where privacy limits what logs can be shared, you fall back to zero-knowledge proofs that the provider's summary statistics match an honest reconstruction within stated tolerances. Each of these steps converts trust us into verify that, trimming the gap an attacker can hide in. None of this pretends side channels can be eliminated entirely. Instead, you bound them and show how those bounds flow into end-to-end guarantees. Your report might say, phase choice is indistinguishable from power traces to within this tiny variation. Back reflections are below that threshold with this confidence. Detector dark counts and afterpulsing sit in these bands. Crosstalk produces at most this correlation across lanes. And your security proof takes those numbers as inputs, not afterthoughts. The result is a composable claim that survives contact with auditors and with time. And if your use case is science rather than cryptography, the same discipline saves you from fooling yourself. Tomography that models context prevents you from mistaking heating for entanglement or calibration drift for exotic dynamics. The gentle lesson underneath is not paranoid, but practical. Reconstruction is a story you ask your device to tell about itself. And clever devices, whether by accident or by design, can tell a tidy story while leaking the plot through the theatre walls. Widen the script, mic the halls, and add ushers who watch the exits, and the same tomography that once gave you false comfort becomes a trustworthy compass. Then, when you send delicate states across a chip or across a city, you do so with eyes open, budget lines explicit, and a calmer mind. Because you have not only seen what your device does when asked the usual questions, you have also checked what it cannot help but say when it thinks no one is listening. Information causality, Why limits exist. You sense the world has rules you cannot bargain with the moment you imagine a friend far away asking you to send just one bit and somehow helping them recover many bits they didn't receive. And information causality is the principle that stops that fantasy before it breeds contradictions. The idea that the amount of knowledge a receiver can gain about a sender's private data is limited by the number of actual, classical answers the sender transmits, no matter what prearranged correlations or shared quantum resources they hold. The hook is operational, not abstract. Picture Alice holding a long list of secret bits and Bob choosing a single index he cares about, then allowing Alice to send him only a tiny message. If nature allowed Bob to learn more than that message seems to carry, you could bootstrap the trick to compress multiple decisions into one and unravel the very bookkeeping that makes communication meaningful. The principle says you can pre-share any allowed correlation you like, classical randomness, entanglement, even correlations that beat classical Bell limits, but once the real message is sent, the total, average gain Bob can achieve about Alice's list is capped by the number of bits she actually shipped. This is why the universe refuses the siren song of non-local boxes that would let distant parties coordinate answers too well. Such super strong, faster than quantum correlations would enable Bob to reconstruct many entries of Alice's list after receiving only a dribble of classical information, smashing the accounting. In that counterfactual world, one bit could do the work of many, and chains of people could collapse complex agreements into single ticks of a wire, breaking the intuition that messages are conserved the way energy is. In our world, quantum correlations are powerful but still respectful. They let you win certain non-local games more often than classical players, yet they stop short of the super strong zone precisely where information causality would otherwise be violated, placing a quiet fence around what entanglement can buy you in communication tasks. What makes this principle useful is how it translates into tests you can run and design choices you can trust. Think of a family of tasks where Bob wants the value of one chosen bit from Alice's long list, and Alice is restricted to sending a short message. Under classical correlations, there's a clear trade. If the message is small, Bob's best strategy can only guess well on a small slice of possibilities. With quantum correlations, their performance improves, but never beyond the line drawn by information causality. With hypothetical post-quantum correlations, performance jumps too high and the line breaks. Thus, by measuring how well a protocol lets Bob recover Alice's data across many random choices, you can certify whether the underlying correlations live inside the quantum set or pretend to be something stronger. This is not simply about physics pride, it is a design constraint for networks and algorithms. If you rely on pre-shared entanglement to save bandwidth in a verify-approver system, information causality tells you exactly how far the savings can go and where you must pay with actual transmissions. In coding theory, it blocks impossible schemes that would promise miracle compression with tiny side messages. In privacy, it bounds how much a curious server could learn about your database from cleverly crafted queries plus a sliver of feedback. And in complexity, it illuminates why certain communication problems stay hard despite quantum help. The pre-shared magic improves the odds, but cannot mint extra bits of influence out of thin air. The deeper comfort comes from how this principle harmonizes with other pillars rather than fighting them. It fits with no signaling, because if messages carried more knowledge than their size, you could stitch together networks where information sneaks around purely through correlations. It respects the Holevo bounds message-to-knowledge ratio for quantum carriers by declaring that even with entanglement on the side, the classical information extracted at the end is governed by what was actually sent. And it aligns with thermodynamic bookkeeping, because if you could squeeze many reliable decisions through a single bit consistently, you could beat the ordinary costs associated with recording, erasing, and resetting, rearranging entropy budget lines in ways that would make engines look too clever. Importantly, information causality does not claim that all tasks are equally limited, shared. Correlations can steer which facts a receiver learns more efficiently, but the sum total of advantage across independent questions never exceeds the true message budget. Think of it as a ledger. You can move credit between accounts with smart correlations, but the grand total never surpasses the deposit. Critics sometimes ask whether this is a definition disguised as a law. Perhaps the world simply picked the quantum strength by other reasons, and information causality is a rephrasing, and that healthy skepticism spurs refinements. Researchers derive concrete inequalities from the principle that match exactly the boundaries observed in quantum experiments. They show that allowing any stronger than quantum box would enable absurdly good random access coding, where one bit of communication routinely yields many reliable answers, and they connect the same limits to the geometry of allowable correlations, revealing that quantum theory sits in a convex body shaped precisely to keep information accounting sane. When you vary the rules, letting the sender and receiver share stronger resources, or redefining which questions count as independent, you can trace how the principle bends, and in each case it continues to act like a speed limit for knowledge transfer rather than a mere slogan. In practice, the lesson leaks into engineering habits. When you design protocols that exploit pre-shared entanglement to reduce bandwidth, you check your promised gains against this upper bound. When you analyze the leakage of a database that responds to short queries, you treat every extra hint you send as consumption of your information budget, and refuse to believe gains that exceed that account. When you model new physics, or propose exotic devices with non-local behavior, you run them through information causality tests to ensure they don't silently permit multi-answer recovery from single coin messages. And when you teach students why quantum is powerful yet disciplined, you show them that the very correlations that feel mysterious stop exactly where violating them would turn communication into a magic trick. The soft image to carry away is not a forbidding wall, but a clean balance sheet. You and your partner may share patterns that help you coordinate across distance, but the amount of learnable detail that crosses between you still tracks the number of answers you actually send. If you try to claim otherwise, some other part of your story, no signaling, thermodynamics, or the geometry of correlations, will disagree. And that coherence among constraints is why limits exist at all. Not to dampen imagination, but to keep promises compatible, so that when you design with quantum resources, you know exactly which miracles are offered and which temptations are mirages. Hold that clarity, and the principle of information causality becomes less a stern rule and more a quiet guide that lets you push to the edges of what's possible without stepping off the map. Thermal versus entanglement entropy. You can feel the difference between two kinds of disorder by imagining the same room twice. First, buzzing with warm air where molecules dash unpredictably, and second, perfectly cold but filled with two choirs on opposite balconies singing in such tight counterpoint that either choir alone sounds like noise while together they make a precise harmony. And that contrast is the heart of thermal versus entanglement entropy. The first measures ignorance about which microstate a genuinely hot system occupies. The second measures how much a pure, fully known state looks mixed when you only hold a piece of it. In a thermal story, you attach your system to a bath, wait, and then count how many micro-configurations are consistent with the macroscopic facts you control: energy, volume, particle number. So the entropy scales with how many ways matter can be arranged while still feeling the same to your coarse instruments. Raise the temperature and you truly pump in energy that gets spread across modes. So adding particles and enlarging the system increases entropy roughly with the amount of stuff you have. This is a volume law, not because of math fashion, but because every additional region brings its own independent rattling. By contrast, entanglement entropy appears even at absolute zero. With no heat and no ignorance about the global state, you pick a subsystem, left half of a chain, a patch of a lattice, a chunk of space, and ask how mixed its reduced description becomes when you ignore the rest. A ground state of many-body matter can be perfectly pure overall, and still look noisy locally because information is stored in correlations across the cut, not as thermal agitation. The most startling fact is that typical low-energy states obey an area law. The entropy of a region scales with the size of its boundary, not its volume, because only degrees of freedom near the cut are strongly entangled across it. Gaps in the spectrum suppress long-range correlations, keeping entanglement focused at the interface, whereas at critical points, where correlations stretch, this area law picks up slow. universal corrections that betray the underlying field theory. In metals, insulators, topological phases, and even exotic spin liquids, that boundary scaling and its fine structure become fingerprints you can read without heating the sample at all. Thermal entropy has direct workaday meaning. It tells you the maximum useful work you can't extract because energy has been scrambled, the cost you pay when you erase memory, the irreducible waste heat your engine must dump. You can measure it calorimetrically. You can move it with heat pumps. You can trade it against free energy when you design a battery. Entanglement entropy's meaning is quieter but just as concrete. It bounds what local observers can learn without reuniting parts. It sets limits on compression schemes that try to simulate many body ground states with few parameters. It governs how complex a quantum circuit must be to prepare a state from scratch. And it underwrites the efficiency of numerical methods that cut systems into pieces and stitch them back. With low entanglement, matrix product and tensor network methods thrive. With high entanglement, they choke, and the computation tells you why a physical phase is simple or stubborn without asking you to draw every amplitude. The two entropies meet but do not merge in isolated systems driven far from equilibrium. Prepare a complex many-body state, let it evolve under its own interactions, and small regions often relax to behave as if they were in contact with a heat bath at some effective temperature, even though the whole state remains pure. This is the content of the modern eigenstate picture. Typical high-energy eigenstates already contain enough internal complexity that any small part looks thermal, so entanglement growth after a quench becomes the mechanism by which subsystems acquire thermal-looking entropy, while the global wave function stays perfectly coherent. The spread is not magic, but transport. Local interactions propagate correlations outward in a light cone-like front, turning initially simple product states into ones where cuts slice ever more shared structure. In integrable systems and many body-localized phases, that spread is muted or arrested, and the saturation value and scaling of entanglement differ, signaling that conventional thermalization fails. This is where distinguishing the two notions saves you from confusion. A system may show rising entanglement entropy of parts without any heat flow from an external bath. And conversely, a truly hot mixed state may have little useful entanglement at all between widely separated regions. Its entropy is classical-looking ignorance, not quantum sharing. Geometry makes the difference tactile. Draw a boundary around your subsystem and you are essentially drawing the budget for entanglement entropy. Because the cut counts, links you sever. Widen the region while keeping shape, and the boundary grows more slowly than the volume, explaining why ground state entropy is modest, even in large samples. Heat the system and the counting changes. Every new bulk degree of freedom can carry independent randomness, so thermal entropy grows with size. In lattice models, this contrast separates phases that tensor networks can handle from those that defeat them. In ultra-cold atom experiments, it separates low-entropy Mott regions with sharp edges from thermal clouds, and in photonic platforms it separates engineered cluster states with boundary-structured correlations from bright thermal light with featureless noise spread everywhere. There are subtler signatures too. Topological entanglement entropy appears as a small, negative offset to the area law in certain ordered phases, protected not by symmetry breaking but by global patterns. You can read out a number that counts hidden quantum types without heating, something no conventional thermometer can show. In contrast, thermal entropy tends to drown such fine structure unless you cool close to the regime where those patterns dominate. Across the quantum materials landscape, mapping the dependence of entanglement on region shape, size, and subsystem choice has become a non-invasive spectroscopy of order, while measuring heat capacities and equation of state data maps the thermal landscape. Each tool learns what the other cannot. Operationally, you manipulate the two entropies with different levers. To lower thermal entropy, you couple to a cold bath and wait, or perform algorithmic cooling that pumps heat out via engineered cycles. To lower entanglement entropy, you change Hamiltonians, cut couplings, perform measurements that collapse correlations, or flow through a quantum circuit that disentangles by design, Measurements themselves blur the line. A sequence of local readouts can cool entanglement by projecting out shared structure even at fixed energy, while weak continuous monitoring can create a competition between unitary growth of entanglement and measurement-induced pruning, yielding dynamical phase transitions where the steady state flips from volume law to area law entanglement purely by changing how often you look. Nothing about that is thermal in the classic sense. Yet the language of entropy still guides your intuition about what information survives. The difference also surfaces in promises and costs. Thermal entropy is tradable for work, with exact prices set by temperature and free energy gaps. Entanglement entropy is tradable for capability, better teleportation fidelity, improved sensing beyond classical limits, stronger error-detecting codes, with prices set by how much non-local structure you can maintain in the face of noise. When noise creeps in, both entropies entangle, in the ordinary sense. In the accounting, local dephasing that destroys phase relations injects thermal-looking mixedness into the reduced state, increasing both the classical ignorance of parts and reducing the useful quantum sharing across the cut. Engineers diagnose which dial moved by changing the partition. If entropy changes with region size like area, they suspect decoherence at boundaries or measurement backaction. If it changes like volume, they suspect heating or particle loss. This diagnostic works in chips, atom arrays, and even biological analog models where coherence competes with dissipation. Perhaps the cleanest way to carry the distinction is to see the two entropies as answers to two different questions you will actually ask. Thermal entropy answers: how many micro-possibilities compete with equal rights given the macroscopic facts I control? And what work am I forbidden to extract unless I push heat somewhere else? Entanglement entropy answers: how much of the world outside my cut must I touch to recover the order hidden in what I hold? And how hard is it to simulate or reshape this state without paying an exponential price? Confuse them and you will think a cold, highly entangled ground state is messy in the same way a warm gas is messy. Or you will imagine that heating a system automatically creates useful quantum resources. Keep them separate and you gain a map. Boundary versus bulk, correlation versus ignorance, capability versus thermodynamic cost. Then the phenomena that first seemed paradoxical. Pure states with locally high entropy, hot states with little non-local power, quenches that thermalize subsystems without a bath, become consistent chapters in a single narrative. Entropy is not one thing. It is a family name, and the given name, thermal or entanglement, tells you which ledger you are balancing and which promises you are allowed to make. Page curve and information return. You first feel the strangeness of gravity's bookkeeping when you imagine tossing a diary into a black hole and asking not whether it is gone, that's the old fear, but whether in principle the diary's information can ever come back. And the page curve is the cleanest way to think about that question. Track the entanglement entropy of the radiation that leaks away as the whole evaporates. And if the world is unitary, if quantum evolution never truly destroys information, that entropy should rise for a while and then fall, returning to zero by the time the whole is gone. Hawking's original calculation gave a different story, a steady climb to the end that would leave the radiation forever mixed and the diary's details forever lost. But that calculation treated the near-horizon region as if it were emitting independent thermal quanta with no long-range bookkeeping. And the page curve says that cannot be the whole tale. Early on, each outgoing quantum is nearly thermal and mostly entangled with degrees of freedom still inside. So the radiation's fine-grained entropy grows, exactly as your intuition from a hot surface would suggest, but after enough quanta have escaped, around the page time. When roughly half the black hole's initial entropy has been radiated, the balance must flip. New radiation should be more entangled with the earlier radiation than with what remains inside, so that the combined outside system starts to purify. By the end, if evaporation is unitary, the full radiation field sits in a pure state whose subtle, long-range correlations encode the diary perfectly, while the whole has no secrets left to hold. This sounds like magic until you remember two things you've already learned elsewhere. First, entropy is always about what you can see when you trace out the rest. And second, correlations can hide structure from any local probe. The page curve is just that logic applied to horizons, with gravity's extra ingredient that the very notion of inside and outside can shift when you ask what surface actually extremizes a certain entropy functional. Modern work makes this precise, with the idea of generalized entropy, ordinary, entanglement entropy of fields, plus an area term that counts microscopic degrees of freedom of geometry, and with islands and quantum extremal surfaces that determine which regions contribute to the entropy of what you, the distant observer, can reasonably access. Before the page time, the extremal surface hugs the horizon and no island sits in your ledger, so the radiation's entropy rises in step with the outgoing thermal look. After the page time, a new saddle takes over. An island inside the black hole enters the calculation, and the formula tells you to include those interior degrees of freedom as if they belong to the radiation's entanglement wedge. That switch changes the slope from positive to negative without ever breaking locality in the lab. It is a statement about which correlations are counted, where when you insist on a consistent quantum gravitational accounting. If that sounds abstract, focus on what it forbids and allows. It forbids any late-time picture in which each photon you detect is independent of the early ones you recorded. It insists that subtle, high-order correlations are present across the entire radiation field, correlations that a thermometer would miss, but that a godlike decoder could exploit to reconstruct the diary. It allows the near-horizon physics to look essentially thermal to any local measurement while still being globally pure, once you gather enough of the radiation and process it cleverly. There is no contradiction, because thermal looking and globally pure are questions asked at different scales and with different cuts. The island rule is the bridge that keeps the answers compatible. You can give this story operational teeth with two thought experiments that point in opposite directions. The Hayden-Preskill mirror tells you that if a black hole has already passed its page time and is a good scrambler, then throwing in one more diary page is not a death sentence. The information flows back out surprisingly quickly, mixed into a modest amount of additional radiation, provided you already hold the early radiation and can perform a heroic decoding. The complement is the AMPS puzzle about firewalls, which highlights the tension between monogamy of entanglement, late Hawking quanta cannot be maximally entangled both with interior partners and with early radiation, and the smoothness of the horizon. The island picture resolves the entropy bookkeeping, but leaves you with an honest message. Some cherished low-energy assumptions cannot all hold at once globally, and deciding which one fails is a matter of precise conditions and observers. What never fails, according to the page curve story, is unitarity. You might ask how a low-energy observer could ever see this purification, and the practical answer is that they cannot without extraordinary resources. Decoding the late-time correlations is believed to be computationally hard, and the required joint measurements over vast radiation modes are unkind to real detectors. Yet difficulty is not impossibility, and physics draws the line at principle, not convenience. The page curve does not promise an easy recovery of secrets, only that no consistent theory lets the secrets vanish absolutely. In holographic models where gravity in a bulk is dual to a well-behaved quantum theory on a boundary, the principle is even cleaner. Boundary unitarity guarantees a page curve, and the gravitational derivations with replica wormholes and islands simply show how semi-classical gravity learns to respect that guarantee when you ask the entropy question the right way. In that language, the emergence of an island after the page time is the bulk avatar of an algebraic fact in the boundary theory. Which degrees of freedom are reconstructible from which region has changed with time, and the entanglement wedge of the radiation has grown to include parts of what you naively call the interior. None of this erases thermodynamics. Coarse-grained entropy, heat flow, and Hawking's temperature remain excellent guides for local processes. The page curve simply insists that fine-grained entropy, the exact information ledger, obeys a different arc because the radiation is not a bag of independent coins, but a woven fabric. Think of it as two dials you can turn independently. One dial sets how hot the local spectrum looks, the other tracks how entangled the global state is with itself. At early times, the hot look and rising entanglement go hand in hand. At late times, the hot look can persist locally, while global entanglement is quietly being repaid, stitch by stitch, to the outside world. There are lessons you can carry beyond gravity. Any strongly scrambling quantum system that sheds excitations into an environment can show page curve-like behavior when you ask about the entanglement between the emitted quanta and the remainder, and the tools developed for black holes, random unitary models, out-of-time order correlators as scramblers speedometers, and the language of quantum error correction mapping interior operators to exterior reconstructions have become lenses for complex many-body dynamics. Likewise, the very idea that what counts as inside can shift with the observer's access is now a standard moral. Information is not tied to a place, it is tied to a reconstruction ability defined by the algebra of observables you control. If you want one picture to hold in your mind, imagine plotting a single graceful arc, from zero to a peak and back to zero, with the peak marking the moment when the outside world knows as little as it ever will about the diary's fate. Before that summit, you are in the Hawking regime. Each photon looks thermal, memory is being hidden behind the horizon, and entropy rises. After that summit, you're in the Page regime. Each photon still looks thermal up close, but collectively the stream begins to return knowledge as correlations knit across distances. The whole shrinks. The island grows in your ledger. And by the end, nothing remains to hide the diary's story except the difficulty of reading it. This, in the softest terms, is information return. Not a burst of memos, but a quiet reweaving. A promise that the universe keeps better books than a first glance suggests, and that when you phrase the question with the right cut and the right notion of entropy, the answer bends toward unitarity with a curve that has, by now, become a signature of how gravity and quantum mechanics share the same ledger. Petz map. Undoing loss. Mathematically. You only appreciate how forgiving quantum mechanics can be when you learn there's a principled way to walk backward through certain kinds of noise, and that recipe is the Petz recovery map, a state-aware, mathematically clean procedure that says, if information about your system wasn't truly destroyed, but merely scrambled by a known physical process, then relative to a chosen reference snapshot, there is a canonical way to unscramble it and, in important cases, get everything back. To feel this without equations, imagine three ingredients: a channel, the noisy evolution you suffered, a reference state, your best baseline picture of typical inputs, and a promise from nature called the data processing rule. Coarse graining can't increase how distinguishable two states are. Whenever that promise is tight for your pair of states, meaning the channel did not actually blur them more than strictly necessary, the Petz map is the unique, gentle reversal that restores the original distinctions with no extra damage. It is like Bayesian undoing for quantum processes. You weight what came out by how expected it was under the reference. You rewind the physical steps in the only consistent way, and you renormalize so the answer is a valid state, all without peeking at which specific input you had. Crucially, the recovery is state-dependent, not a universal undo button. You commit to a baseline distribution of inputs, and the Petz procedure is optimal for that baseline, much as a perfect classical decoder is tuned to a known source. This state awareness gives the construction teeth. Use the right reference and you invert dephasing that struck a code subspace, or you resurrect delicate phases after a measurement-like disturbance. Use the wrong one and you still recover something, but not the jewel you wanted. A reminder that no map can conjure information that was truly erased rather than hidden. The power of Petz recovery first appeared as a characterization of when a channel loses nothing. In an information theoretic sense, if the distinguishability between two inputs survives the noise exactly, a rare but telling situation, then the Petz map built from those inputs, and the channel will send the outputs right back to the inputs. Proving the channel was sufficient for that pair. Later, the idea blossomed into a metric for partial reversibility. Even when the promise isn't tight, a nearby rotated version of Petz recovery guarantees a minimum overlap between what you reconstruct and what you started with turning vague hope into a quantitative flaw. This is the content behind modern, approximate recovery theorems. The more the channel's action preserves relative structure, as witnessed by small drops in distinguishability, the better a Petz-style map can do, and the inequalities make this precise without a single pulse sent to the lab. Operationally, that means you can certify, just from measured statistics, that your data is recoverable to a certain fidelity by a concrete, efficiently describable map, instead of trusting a custom neural decoder or a mysterious variational circuit. The Petz map becomes not only a concept, but an algorithmic fallback with provable performance. To anchor the intuition, picture a dephasing environment that partially forgot the phase relation between two basis states. If your reference state has support across the same subspace and encodes the same notion of typical, the Petz recipe instructs you to rescale amplitudes the way Bayes would, apply the time reverse of the channel relative to that baseline, and re-weight the answer. Physically, you correct phases and populations in just the proportions the noise would have skewed for the reference. For amplitude damping, the archetype of spontaneous emission, the same logic yields a recovery that first tilts probabilities to undo the bias toward the ground state and then applies the channel's adjoint actions in a carefully balanced way. In neither case do you need to know which pure state you had. You only need the channel and the baseline, and the map treats all compatible inputs fairly. That is why Petz recovery sat quietly for years in the mathematics of quantum statistics, where it formalizes sufficiency in quantum Markov structure, and then surged into engineering. It told error correction designers when a noisy block behaves like a conditionally reversible step, and gave them a closed-form decoder to try before heavier numerics. The same construction speaks to thermodynamics with unusual clarity. If you take the Gibbs distribution at a fixed temperature as your reference, the Petz map becomes a physical time reversal weighed by that thermal baseline, and the inequalities bounding recovery translate into second-law refinements. Quantitative statements of how much free energy or a thermality you can reclaim after a dissipative stroke. When an experiment claims to build a Maxwell demon from clever feedback, Petz-style bounds ask where the missing information went and how much of it is, in principle, recoverable without paying elsewhere. In metrology, the map explains why certain sensing protocols are robust. Channels that barely reduce distinguishability for the signals of interest admit high-fidelity Petz recovery. So you can push fragile probes through a noisy stage and then unscramble them enough to regain sensitivity. In open systems modeling, it underlies the notion of a quantum Markov chain. When three parties satisfy a conditional independence relation, information about one that leaks through the middle can be perfectly pulled back by a Petz map. This is not poetry, but a structural signature, used to diagnose when a bath really is memoryless and when it only pretends to be. Of course, the map is not a panacea. It won't reverse genuine erasure where distinct inputs collapse onto the same output for your reference, and it inherits every blind spot of that reference. Choose a baseline that ignores rare but important inputs, and those inputs become unrecoverable by design. It also assumes you know the channel well enough to build its adjoint actions. A fair demand in calibrated devices, but a challenge in the wild. Here, practice answers with learned Petz. You estimate the channel and the baseline from tomographic data with side channel audits so your estimates aren't biased. Then instantiate the recovery and test it on held out states. Often, a small rotation around the canonical recipe, averaging over phase twists theorems tell you about, boosts performance and smooths model errors. The remarkable part is that success is certifiable. The same information inequalities that motivated the map give you experiment-side bounds on the fidelity you achieved, not just a reconstruction picture, no black box, no ungrounded claims. The map's reach extends into resource theories and learning, coherence, asymmetry, and magic, the fuel for non-Clifford gates, are all monotones that drop under noise. Petz-inspired recovery quantifies how much of each you can, in principle, reclaim, given a free operation model and a baseline ensemble. Turning hand-wavy, maybe we can post-process into explicit exchange rates in reinforcement-like settings where you apply sequences of controls while a system drifts. Rolling Petz recovery Into the Loop provides backward passes that estimate how much of the recent degradation is reversible versus truly lost, guiding where to spend limited calibration time. And in communication, Petz decoders sit beside maximum likelihood and belief propagation tools. In channels with structure, e.g., dephasing dominated or thermally biased, the Petz choice is not merely principled, it is competitive, often beating heuristic filters because it embeds the right notion of time reversal for that noise. Experiments have started to put skin on these bones. Trapped ion setups have demonstrated Petz-like reversal after engineered dephasing by conditioning on a well-characterized baseline and applying adjoint gates. Superconducting circuits have used rotated Petz maps to partially reverse amplitude decay over short windows, with performance lining up with theoretical bounds. Optical platforms have implemented Petz-inspired filters in Gaussian channels, showing that state-aware inversion outperforms blind deconvolution at equal photon budgets. In each case, the takeaway is less "we did magic" and more "we picked the one mathematically canonical undoing and it worked as promised within the noise model's truth." If you want a compact mental picture, keep this. Petz recovery is the quantum analog of Bayes with memory. Given a forward blurring and a prior, it gives the single most honest reverse blurring that restores the distinctions your forward step did not truly destroy. It tells you exactly when perfect undoing is possible, when distinguishability didn't drop, and how close you can get when it did, via robust fidelity flaws. It turns recovery from an art of bespoke decoders into a science of guaranteed decoders. With levers you can name, reference choice, channel estimate, rotated averaging, and dashboards you can audit, measured distinguishability loss in, certified reconstruction out, and it teaches a steadying lesson. Loss in quantum mechanics is not a monolith, but a spectrum from reversible scrambling to irrevocable collapse, and the Petz map is the line you throw into that spectrum, not to promise miracles, but to recover everything that physics still allows, with proofs to tell you when you've reached the limit. Complexity as a physical resource. You realize that hard is not just a feeling, but a fuel the day you watch two tasks that use the same atoms, the same energy, and yet one blooms effortlessly while the other stalls until you budget more steps, more memory, more careful control. And that is the doorway into seeing complexity as a physical resource. Not a metaphor about messy things, but a measurable stock of organized effort that determines which transformations are available to you and at what price, just as energy and entropy already do. Start with the simplest picture. A quantum device begins in an easy state, and you drive it toward a target by applying elementary moves from a fixed toolbox. Each move is a gate, a pulse, a reversible nudge, and the circuit depth to get close defines the state's complexity relative to that toolbox. Cheap states sit near the origin in this landscape. Exotic states lie far away, and the geometry between them is not Euclidean, but carved by what your hardware can actually do quickly. This is why physicists talk about geodesics of computation. The shortest feasible route through the space of allowed moves is your optimal recipe, and anything longer is wasted life. What makes this physical, rather than purely algorithmic, is that every step carries costs. Time your system must remain coherent. Power your control lines must deliver. Calibration you must maintain against drift. So complexity becomes the exchange rate linking abstract goals to laboratory budgets. More startlingly, many body systems behave as if they obey an almost thermodynamic law of complexity growth. Starting from simple conditions, they scramble, spreading local structure into global detail, so that the minimal number of steps to reverse them rises roughly linearly for a long time before saturating near a colossal maximum. Black holes are the poster child in theory. They appear to be near optimal scramblers, ramping up complexity at the fastest rate allowed by quantum speed limits, so much so that people now speak of second laws of complexity, arrows of time, defined not by heat but by how far a state has drifted from easily reachable shores. If you could drain that complexity, you would not extract energy. You would extract undoability, turning a tangled evolution back into order with a budget of steps that no shortcut can beat. To make this operational, separate three meanings that often blur together. Descriptive complexity, how short a classical program can describe an object. Computational complexity, how many steps a procedure needs to solve a problem. And state or unitary complexity, how many physical moves prepare or enact something in a given lab. They rhyme but do not coincide. A string that is incompressible in the descriptive sense may still be easy to produce by a physical process designed for that pattern, while a state that looks random to a microscope might be a few clever pulses away if your controls align with its structure. This mismatch is not a bug, it is the point. Complexity is always relative to a model of action, so the right question in a device is not, is this state complicated in the abstract, but how far is it from my starting point under the moves I can implement with high fidelity? Once you adopt that stance, familiar limits acquire new teeth. Quantum speed limits bound how fast distinguishable states can be reached given your energy spread, thereby bounding how fast complexity can grow. Control theory bounds how tightly you can steer with finite bandwidth, imposing a precision budget. Extra digits of accuracy are costly, and the price explodes once you push beyond your hardware's sweet spot. Error correction converts raw steps into reliable steps at the cost of more steps and more qubits. So logical complexity is physical complexity, multiplied by an overhead you must engineer down. And thermodynamics does not disappear in this story. Erasing classical side information or refreshing ancillas to keep a long computation tidy still costs heat, so the currency of complexity trades in the same market as energy and entropy, just at a different counter. Complexity also behaves like a permission slip for security and pseudo-randomness. If certain tasks are provably hard for any efficient adversary, you can build locks whose strength comes not from secrecy about the mechanism, but from the cost of the best attack. Quantumly, families of states and unitaries can be made to look completely generic to any short experiment, while being constructed by specific deep circuits. This is why pseudo-random states and unitaries matter. They are cheap enough to prepare with a long but feasible recipe, yet expensive to distinguish from ideal randomness without a longer recipe still. The gap is a resource that fuels protocols, from copy protection of quantum software to traps for outsourced computation, where the guarantee reads, "No one can do this without paying at least this many steps." In physics proper, complexity creates phase diagrams beyond temperature and coupling. Shallow circuits prepare low-depth phases with short-range structure, while certain orders, chiral, fracton-like, or with intricate constraints, require depth that grows with system size no matter how cleverly you schedule, marking them as inherently costly to assemble. Drive a system while measuring parts of it, and you can witness complexity transitions. Below a critical rate of measurement, dynamics keep generating novel structure and minimal circuit depth inflates with time. Above it, observations prune structure faster than it accumulates, and depth saturates early, an arrow you can flip, not by cooling, but by changing how often you look. Where gravity meets computation, the story becomes unexpectedly literal. Conjectures relate the volume or action of certain regions behind horizons to the boundary state's complexity, suggesting that what grows behind the horizon as time passes is exactly the difficulty of reconstructing the boundary's evolution with simple gates, though still under debate. This picture gives a concrete operational reading to slogans about wormholes as circuits, and ties complexity growth to causality, chaos, and the limits of decoding. One more sign that complexity is not a spreadsheet artifact, but a geometric feature of how information arranges itself in physical law. Even in tabletop systems, echoes abound. Out-of-time order correlators track the early rise of complexity by measuring how quickly simple operators spread into complicated ones. Random circuit models show a linear light cone in which complexity advances like a front, and noise creates attacks on attainable complexity, because every additional layer risks washing out what you built. Unless protected by overhead, you must pay in qubits and time. Treating complexity as a resource rewrites everyday engineering choices. Compilers stop counting only gates and start counting structured gates that align with hardware-native moves. Schedulers budget concurrency to reduce depth without increasing crosstalk beyond safe limits. Architects place factories for difficult resource states next to the modules that demand them to amortize long stretches of depth. Calibrators track not just fidelity, but the marginal cost of an extra decimal of precision, so teams know when to stop tuning and start redesigning. And theorists express algorithm promises with volume-time targets. How much space and how long a road you must walk in the landscape of allowed motions to reach an answer with high confidence. Crucially, these budgets compose. When you stitch devices into networks, the end-to-end complexity includes communication steps. When you add verification, it includes challenge rounds. When you add privacy, it includes blinding masks. The complete bill is not a footnote, but the thing you must meet to make a system real. Perhaps the clearest way to carry all this is to adopt a craftsman's view. Energy tells you whether a transformation is possible at all. Entropy tells you how costly it is to concentrate order without dumping heat. And complexity tells you how demanding it is to express the transformation with the moves you are allowed. A low-energy, low-entropy task can still be beyond reach today if its minimal recipe is too long for your coherence time, too deep for your error budget, or too precise for your calibration tools. Conversely, a task that looks forbidding may become easy if you change the basis of allowed moves, switch encodings, exploit symmetries, or reshape the geometry so the geodesic shortens. Complexity is therefore both a constraint and a design compass. It limits you when you ignore it and guides you when you honor it, pointing to hardware that natively implements the long patterns your workload needs, to algorithms that trade width for depth in friendly ways, and to protocols that turn hardness into strength. Hold that compass and the world's hard problems stop being walls and start being mountains with roots, some long, some short, all measurable, so that progress is not a mystery, but a steady conquest of distance in the space of what you can do. Quantum memories, spin, ion, and photon. You understand what it means to remember without touching when you meet a quantum memory, a device that holds a delicate state long enough for the rest of the world to catch up. And the landscape divides naturally into three temperaments: spins that keep secrets in the quiet procession of a microscopic compass, ions that cradle information in hyperfine notes inside an immaculate vacuum, and photons that insist on moving at light speed until persuaded to pause inside matter for a breath. To feel why we need all three, picture a network that must synchronize events separated by imperfect links. Photons are the couriers that travel, ions are the vaults that compute and coordinate, and spins are the archives close to the hardware's heart. And the craft is to store, retrieve, and transform states without letting the story smear. Spin memories make their case with stillness. A single electron or nuclear spin in a solid. Silicon dopants, color centers in diamond, donors in germanium, precesses like a tiny clock whose tick can last milliseconds to minutes when you isolate it from jittering neighbors and magnetic hiss. This longevity is purchased with materials discipline, high purity, isotopic engineering to quiet nuclear clutter, low temperatures to reduce vibrations, and with dynamical decoupling, a pulse rhythm that refocuses wandering phases the way a metronome steadies a chorus. Electron spins talk to light and microwave lines with ease, which makes them agile, while nuclear spins, slower to respond, are the deep vaults. You swap the fragile electron state into the nucleus to park it, then swap it back when needed. In labs, ensembles of rare earth ions embedded in crystals offer another spin-flavored memory. Their optical transitions are narrow and stable, and their inhomogeneous spread can be turned from a nuisance into a feature by shaping it into an atomic frequency comb that catches and later re-emits a photon with programmable delay. You get a memory with strong multimode capacity, able to hold many time bins at once for multiplex networks. The trade-offs are honest. Spins integrate well with chips and benefit from mature fabrication, but they need careful calibration, magnetic shielding, and often cryogenics. Their bandwidths can be modest, and interfacing them to telecom wavelengths, the language of long fibers, usually requires frequency conversion stages that add complexity and potential noise. Ion memories, by contrast, lean on cleanliness rather than quietude. A handful of charged atoms levitated in electromagnetic fields inside an ultra-high vacuum chamber present nearly identical copies of nature's best two-level systems. Laser cooling removes almost all motion. Hyperfine states define extraordinarily stable qubits. And coherent control is surgical, single and 2-qubit gates, shelving in metastable levels, state-dependent fluorescence for readout. For memory duties, ions excel at on-demand retrieval with high fidelity. You can store a photonic qubit by mapping it onto an ion via absorption, assisted by cavity enhancement, or by heralded entanglement, where a photon emitted by an ion interferes with a partner from another node. Once the state lives in the ion, you can wait milliseconds to seconds with dynamical decoupling and magnetic field stabilization, then convert it back to light when the rest of the network is ready. And because multiple ions can be parked in a chain, you gain small-scale buffers that reorder, fan-in, or fan-out stored states according to the protocol's needs. The price is apparatus. Traps demand stable lasers, fast switching, and transparent low-vibration environments. Scaling asks for segmented electrodes, photonic interfaces integrated near the ions, and clever ways to avoid crosstalk when many channels are active. Yet the virtue is precision. Ions give you memories that are both long-lived and programmable. With error bars you can audit through repeated calibration and spectroscopy. Photonic memories begin with a paradox. Light refuses to sit still, and that is exactly why we value it. To persuade a photon to pause without destroying its quantum identity, you make matter coherently share the photon's pattern so that later, when you dial the control fields, the pattern re-radiates as if time had held its breath. In practice, this looks like electromagnetically induced transparency, EIT, in cold atomic clouds or warm vapor cells, where a strong control beam opens a transparency window and slows light to a crawl. Switch the control and the photon's shape maps into a collective spin wave across many atoms to be retrieved on demand by turning the control back on. Or it looks like off-resonant Raman schemes that trade some efficiency for wider bandwidths and less sensitivity to noise, storing ultra-fast pulses with tunable delay. Or, as in the rare earth crystals, the carefully prepared frequency comb that catches and re-emits after a set interval, optionally with on-the-fly control that turns a fixed delay memory into a truly programmable buffer. The great strengths of photonic memories are bandwidth and multimode capacity, time bin, frequency, and even spatial multiplexing can be stacked so that one device holds dozens to thousands of modes. A precious ability when you want many attempts in flight simultaneously to raise the probability that at least one will succeed. The challenges are signal to noise, spontaneous. Emission and four-wave mixing can sprinkle unwanted photons into the channel if control fields are not exquisitely aligned, and wavelength most sources and detectors like near-infrared or visible light, but long fibers prefer telecom bands. So frequency conversion stages must be low noise and mode preserving, or the very act of bridging distances erases the rememberable structure. Progress is steady. Cavities boost light-matter coupling, so you can store and retrieve with high efficiency at the single photon level. Waveguides in lithium niobate and silicon nitride bring the control pulses on chip, and hybrid devices couple spin ensembles to microwave resonators so that superconducting processors, fast but forgetful, borrow optical memories as their pause button. Underneath the platforms runs a common scorecard that tells you which memory suits which job. Efficiency asks how much of what you store comes back as usable signal. Fidelity asks whether it comes back with the same quantum character, judged by interference visibility and state tomography. Coherence time asks how long you can wait before phases drift intolerably. Bandwidth and spectral acceptance ask how broad and how fast your pulses may be. Multimode capacity asks how many distinct messages can be parked without crosstalk. On-demand control asks whether you choose the readout time freely or accept a fixed delay. And interface compatibility asks whether your memory speaks the right wavelength and spatial mode for the rest of the system. No single platform wins every category, which is why the field builds hybrids. ion or spin nodes for reliability and logic, photonic highways for reach, ensemble memories for throughput, and frequency converters and cavities as translators and amplifiers of light-matter dialogue. The honest physics behind failure modes is as important as the headline numbers. Magnetic noise scrambles spin precession unless you stabilize fields and use isotopes with quiet nuclei. Motion-induced dephasing in atomic ensembles blurs the spin wave unless you cool or trap atoms or choose Doppler-free geometries. Spectral diffusion in solids moves transitions around on slow timescales, unless you lock the environment and operate far from charge noise. Control pulses must be strong enough to open storage windows, but not so strong that they inject noise. And every extra optic or converter in the path adds loss that an adversarial audit will count against your final fidelity. Wrestling this into a dependable device turns a lab trick into engineering. Active feedback that keeps resonance where it should be. Calibration routines that measure and cancel slow drifts. And protocols that time order storage so that fragile states are kept for as short as necessary and in the friendliest memory for that duration. If you step back, a gentle philosophy emerges. Memory is not a single object, but a choreography of when and where to hold structure so that it survives travel, congestion, and waiting. Spins offer a hand on the shoulder of a processor so it can breathe. Ions offer a vault that answers when called, with a ledger of who stored what. Photons offer a river that can be dammed just long enough to route around rocks. And when you weave them, networks stop being raw pipes and become synchronized instruments, capable of staging entanglement across distance, aligning probabilistic events, and letting fragile quantum patterns arrive together at the moment they matter. That is the test of a good quantum memory. Not that it hoards qubits for sport, but that it slows time just enough, with humility and precision, so that the rest of the machine can do something remarkable, and then, without fuss, lets the stored light sing again in the very shape it learned.